Good morning, everyone. Welcome by this session on intra-data products. We have 5 presentations in this session this morning and a roundtable later this afternoon. So we certainly also hope you to be there. My name is Freek van Leijen from Delft University of Technology. And I hand the microphone now to my co-chair, who will be introducing the first speaker, Mario.
Good morning to everybody. So, my name is Mario Costantini. I invite the first speaker, Christoph Giesinger. I hope I pronounce well the name, to start with the first presentation.
Okay, yeah, thank you for the introduction and welcome back now to the first session here on data products and INSAR. So before start, I want to acknowledge my co-authors, which are all from the MPC and the DLR. So we formed this group that is advising and constantly monitoring the Sentinel-1 mission and report on the data quality. And in this role, I'm kind of responsible and person who looks mostly in geolocation, and in this talk I'm going to tell you about what is the status there, what's the interesting bit about the TOPS mode, and what can we do with these interesting test sites that we have in South America, in Argentina, from the CONE people. Okay, so by trade I'm a geodesist, so don't ask me too much about instruments or star focusing kernels and stuff like that, but what I can tell you is exactly where we are. So, and also, let's say in terms of geolocation, we are comparing the star data, range and azimuth to ground truth on the surface. And geodesy, usually we are really looking into the finest detail there. So we always talk about the centimeter rather than meters. So I hope you can convince you that this is sort of useful, and want to show you the status where we are with Sentinel-1 mission. So this picture here shows kind of the current status of the products if you use them as is. This is what you get since about 2014, since Sentinel-1A started. And I mean, this is already, let's say, decent in a sense that it's meeting our requirements. We are at sub-pixel level, although, I mean, the clouds look quite dispersed, and the scale here is some couple of meters, good enough for the requirements. But since these 10 years, we have really started in digging and understanding how these things interplay and how we can clean up the picture there. And what you see here now is where we are currently. So we take into account the orbit, we have calibrated the mission, we know about the physical effects that are happening. So this cleans up the situation here to the centimetric level in the range and maybe some decimetric in azimuth. And our way of transporting this information to the users and make this visible as well, it's interesting actually to simply just look at these layers. This is the ETA product. You probably heard the term around in several of the talks yesterday and also today. So this is what is really showing all the different contributions here in the frame of an SLC of the IW mode, giving you really a visual picture. If you just plot our layers here, it makes visible what is in the ionosphere, what's in the troposphere, what are the solid Earth effects. So totally, you see, this is this meta level difference between the standard and where we can, what we can do, what's the best possible thing with the products. And now in this presentation, I'm not going exclusively focus here on the azimuth component here. You see it's looking good, but there is some subswath differences here, and this is the topic of today. We want to look at it and try to understand this better. Okay, where are we going to do this? These are the sites in South America. They have been put up there by CONE for the Alban-Sao Commission. And the good thing is that these things are really big. And if you think about even C-band and our IW product, we have 20-meter pixels. So the bigger the targets, the better for us. So this is really useful. They put them up in 2018. So we have long data series, and they have never been touched since. So these are stable targets, have been put up once, oriented once, so we can really trace them very reliably throughout all the data stacks of Sentinel-1. And we also used them during the commissioning phase. As of input, we got via the StarCalNet, which is now ESA's way of contributing and managing calibration sites all over the globe. And this is the picture we got there. And I mean, since I've showed you, we have in principle a calibrated mission where immediately we were certain that this, what we see here, this is not Sentinel, this must be something else there. And so Nuno called S1A a dinosaur, but there's even an older dinosaur there in space, which is TerraSAR-X mission, which has this neat capability of really doing 3D geolocation of targets. If you want to know more, you have the paper up there where you can look up the details of the method. But the key message here is we can really do something that is 3D positioning as if you would do the GPS measurement of those targets. So we've ordered several scenes here. These big targets are easy going for TerraSAR-X, couple of data, equated that out for new positions. And if we feed that in our analysis, we see we have consistent methods. Sentinel, TerraSAR, they use the same kind of ETAD-like methods in the background of cleaning up the data, and we achieve already a very good consistency here now, having better coordinates, and this makes it now easier for us to really study what is going on. So we are back, have put the ball back in the field of Sentinel-1. What we believe, what we see here now in this difference plot between S1A and S1C and all those things is more again on the sensor side, so time to investigate. Okay, briefly on the data situation. So we have lots of stacks here, some interesting details here. So ascending, descending, the sides are kind of spaced interestingly, that for two of the tracks, one ascending, one descending, they are kind of in the same big data take of Sentinel-1, which is just split up there in the slices for processing purposes. So they're just a minute apart or so. We can get an image of the first calibration side, and then we sweep over the other one, and the same in the descending. And some other interesting detail is that some of the targets are even in a burst overlap. And I mean, the mission that we have now is, if we take the biggest targets, the 3-meter ones, give us the best quality. Ideally, we can put all this information here, should give us the same position on ground geolocation. This should perfectly coincide if we do understand the mission and everything that is happening here. So, just again, the wrap up. So this is what we have currently. This is where we start out. I will also show this in the plots later, that this is kind of the baseline, the ETAD status, what we do to the azimuth data of Sentinel-1. So it's a bit of the solid Earth, so centimeter to decimeter effect. We have the big ones that are related to the SAR processing that's happening in the IPF, which we can clean up in the post-processing steps to do it more accurate in terms of geometry. And then we have the calibrated mission. So this is where we are. And then we had to put on again our thinking caps. Since we didn't get the picture we would like to have, there must be something else. And the one that's more obvious to look into in terms of azimuth direction is, of course, the ionosphere. We know about that one. Then there is the other one more related again to the instrument in the details, which is the antenna patterns in the azimuth. And we have something that is again more to the processing and the focusing. This is the beam offset time. And I will now go a bit into some detail of these effects and show you the before after if we add those to our processing of the South American side and see what it gives us. Okay, so not a lengthy explanation here, but the basic effect is in principle understood for geolocation. If we do have a slope in the synthetic aperture, in the ionosphere, in the TEC, and this is also then introducing an along track shift in our data. So this should be kind of notable, and the approach for getting this information somehow to as a correction, the more data-driven approach has been mentioned several times, the split spectrum approach. There is pros and cons. The easier one, but not the more detailed one, but computationally more easier, is the one with the TEC maps. It's already kind of part of our system. It was easy for us to extend that one. So for this study, I went with that one. But thanks to George's contribution, we also do have then the same results available from the complementary split spectrum methods. And later on, we'll also be able to compare both approaches against the ground truth. Okay, so not going into too much detail here, but the bigger picture here just shows you where from the coarse resolution TEC maps we would expect gradient signals, and these are just following here mostly the geomagnetic equator here, and then some plus minus 20 degrees north south of that. This is where we at least get information out of the TEC maps, and even there, worst case in C-band, it could be meters, 1 meter or so as a worst case scenario. Okay, so this is now the temporal view, all the data that we have at our test sites. So for illustrative purposes, I just picked here 2 targets. And these are the 2 sites, but they are imaged just with a minute or so of separation. So we can see nicely the red dots here are from the other side here. The other one, the southern one, are the other 2 colors. We get same data here for these 2 guys here, which are just happening minutes apart. And we see here the time series as we would get it, let's say, with eta at current status, best possible thing. And if we add the ionosphere here, just go back and forth a bit. So we really see that this forward modeling here in this particular case, ascending, this is where we have the ionospheric signals in Sentinel data. It's doing something. It's cleaning up something here, especially for the S1A, but it's on the other hand, it's starting to expose something else here on the S1C. So comparing all the different units here, it's also giving us a much deeper view here on what could be general, what is sensor specific. There's always same targets, same coordinates, so it's interesting to have them all side by side. Okay, the next thing here, this is again more related to the focusing, again actually a topic of its own, but the basic message is the IPF uses a very good already analytical description of its azimuth focusing kernel based on a hyperbolic model of ground point to aperture curvature, the Doppler modeling. This really works very well only if we look at the very extremes here at the far range at IW3 and at the extreme edges of the burst along track-wise, so where we have this Doppler, let's say, of 3000 Hertz. This is where we see a sort of mismatch in terms of where the kernel would focus the zero Doppler time. So there is a discrepancy. It's not large, but if you look into the extremes, it can get asymmetric. But the main message here is this is not something that is varying ascending, descending wise that much and so on. It's really something that on the grand global scheme here. So this is one orbit revolution here of Sentinel-1 here, just given for rotation here starting at equator there in the North Pole. So mid-latitudes, depending where you are, it may or may not have an impact. And for this particular site here, so this is where we left off after introducing ionosphere. If we now add in that effect, so it's really millimetric at best. So at least for this particular study site, it's not giving us that much. But if we were to compare all our study sites, which are all over the globe, we do notice a small improvement from this effect. But here it's not that relevant. Okay. At least something we don't have to worry here. Okay, and then the third element, which is also maybe quite interesting here from a fringe perspective here, this is at the antenna patterns. So, and what we mean here in these antenna patterns here, we usually assume that the start is a sort of a perfect sensor, and then over the course of the mission, things are going to happen, like these events that change the characteristics of the antenna in some way. So the most notable one is, for instance, the tile failure we experienced in 2016 for S1A, but also C, D, and even the B unit. Every once in a while, we have lost a TRM, usually at mission beginning somehow. And in these very minute details of the centimeters to decimeters, this does play a role. So this is just the first start here. We will make this more detail later on, but to just get an idea here, these are three main cross sections here of the azimuth pattern here, kind of before the event, after the event, what's the delta? And what we do care in this case is the slope here of the phase here in the along track direction, which gives you some sort of, let's say, abstract number here, a change of degree over degree, some numbers here. This is the scaling factor there. So we do have, in case of the tops, we get this top scaling, positive, negative, changing with the IW from the antenna steering. This is usually around 4 to 3 scaling factor here. And if we put the two guys together, we can get a first idea of the amount of impact here, what we see from the antenna patterns just by accounting a before and after event. So somehow we do have this break in there. Effect is desymmetric. There is some dispersion between the subswaths. In some cases, it's also kind of mitigated, counteracted by the steering. So for S1D, it's sort of flat. Calibration that we already have would kind of capture this. In other cases, it's varying. So just then a bit for interpretation here. So usually we already calibrated the after event situation, like with S1A and D. For the C unit, this whole thing happened later on, and this has some effect now in the interpretation there. So this is where we left off here with the beam offset time. As I said, not much impact. So now if we introduce the antenna patterns here, they really do something again. So for S1A, we kind of move it out here. We get worse in a sense because we have already kind of compensated it in our calibration. Now it's putting the antenna pattern on top, it's doing something. I will show later a bit more detail on how this impacts the individual subswath offsets. So this is where we're actually aiming for. But the interesting bit here, if I go back and forth, is what's happening for the C unit. So here the pattern really does something. And it's not applied here because this is the pre-event data here. We can really see it. And I mean, it's okay, it's not that much, but I don't think it's coincidence. We had somehow a really neat situation here. And after the event, it got dispersed here. So it must have something to do with the event, I believe. And it's not yet fully captured by the antenna pattern, but I think it's worthwhile to look into this kind of, let's say, problems, which we only see now with this very clean data series and stuff. S1D, of course, has not so much data there, but for comparison, it's still interesting to have all of them. Okay, now in the final part, I want to give you kind of more the complete picture now. If we use all the targets, so in all some 20 corner reflectors, we get some averaging effects, some hopefully more cleaner pictures. And I've separated them again into the ascending and descending part. So just not to give you a kind of cluttered image with the signatures of all the residuals, I've then grouped them in terms of a ellipse here that's just showing the average of a particular beam here, and then the spread here 2 times standard deviation, range, and azimuth. So this is essentially where 95% of our residuals are located. And you can really see that. I mean, the ideal situation here, we would really match all these central average values here to perfectly control all the beams. So this is where we left off with ETAT. If we put up then all the cumulative effects we have studied, we do see definitely some impact. It's a bit hard to interpret and study it in this short of time. So just to give you a bit of a metric here, in terms of spread among the different subswaths, we usually improve it by some 12 to 20%, depending on the sensor. Of course, the data of S1D is not that reliable. We don't have that much yet, but it will come. So it's squeezing together our mean offsets. It's doing something. And we also see the impact of the ionosphere here, which is really bringing down the standard deviation. Again, for S1B, as expected, it operated here only till 21. Not so much ionosphere. It's sort of comparable. But again, for the S1C unit, last year's data, we get a nice reduction in the standard deviation. Okay, so this looks kind of meaningful for the ascending. So the descending, different kettle of fish. Here we have the overlapping targets here. So this is in the burst overlap, one burst, just the next one here. If we control and understand the sensor perfectly, we would be able to accommodate everything here. Picture is still a bit diverse. Again, we do note different characteristics a bit of the sensors here. Even the S1B, which we usually consider to be the best unit here, has some large it's relative, but we do have asymmetric offsets, which we cannot really control. So just showing you the corrected picture again. It's doing something, at least it's aligning kind of the sensors here in some sense, but in cleaning up all this variation there, there's still, let's say, some unknowns here, which we have to go further. Almost done. So 2 slides. So the next step briefly. So as I said, we have the tech maps, but we also have the split spectrum, and maybe this will give us some at least improvements again in the standard deviation and see how these methods compare. In this case, they really match each other. There are also cases where the tech maps here, this and the split spectrum, the dots here, give different information. So the tech maps, they only take us that far. We usually believe the split spectrum is the more detailed one, so we shall see. And the other thing is we can really dig deep into this pattern here. So just the example for S1C, we have all the subswaths. It's actually a 2D pattern, and how this is being exploited by Topstar and how to model this. This is one of our questions, if this can start to clean up all the subswath problems we see for S1C, for instance. So to wrap it up, in general, S1 Sentinel-1 has a very good geolocation quality already as it is, so the capability is there. We have a good agreement with TerraSRX. We use standardized methods, kind of ETAT quote, which brings our sensors together. And these large sites here by Conne are really useful to study these effects, of which I've shown you 3 different things. We have collected some detail now. We still have some way to go, and hopefully we'll make another step here. And once we have done that, the way of forwarding this to the user will be then again an evolution, addition of layers probably to the ETAT products. So yeah, thank you very much, and ready for questions.
Okay, so we have time for one question.
Thank you very much for a very insightful presentation. I was wondering, all the effects that you report are effects of how are we correcting the range from the sensor, basically? But your assessment method uses corner reflectors, right? So that means that if you report values in millimeters, that also means that we need to get the position of the corner reflector as at subpixel level. And if you would need to go from a 20-meter resolution in azimuth for Sentinel to, let's say, 2 millimeters, that is 1/10,000th of a pixel. So is that realistic that we have, that we get to that level of precision in the subpixel?
Yeah, so the thing is, for the corner reflectors, this is the kind of proportionality between target size and pixel size. So for these big 3-meter targets, our floor, let's say, the way we can extract these targets from these 20-meter pixels is about equivalent to 5 to 6, 7 centimeters. So this is the signal to clutter radar cross-section based limitation that we face. Therefore, even here, we need the biggest targets possible. And this is why I focused on 3-meter targets here, of which we think from the individual kind of beams we see, we can approach a precision here of 6, 7, 8 centimeters. Yeah. So we can really then start to still see the discrepancies of decimeters among the different beams.
So is it then fair to say that the numbers that you report are not only the corrections, you know, from the whole effect, but also for the individual reflectors and how well you can determine them as ground truth?
Yes.
Right. Yeah.
So this is the, let's say, the full, let's say, end-to-end thing. Orbit, target position, this all plays a role there in this whole comparison.
Right. So that means that at some point we are not able to get any further with additional corrections, since our targets, we cannot determine them better.
I mean, what we can go there is, we do it statistically, right? We measure in time series, repeat pass, we are averaging, assuming it's a random error. We have all the different targets, which should still all kind of the randomness of the target position error itself. So this kind of spatial temporal averaging is kind of also what helping us. So from a single scene, you're right, we are kind of limited by target size, but if you reliably measure the same site over and over again, this is why I really focus on this long mission duration time series.
I think we should move to the next presentation.
Okay, thank you, Christoph. If there are more questions for Christoph, please approach him in the break. Next presentation will be given by Paul Rosen.
Good morning. I am not Eric Fielding. I'm going to be giving Eric Fielding's talk for him today. He's sorry he couldn't make it here. So I'm going to talk about the NISAR urgent response products for natural hazards and disasters. NISAR is a mission that launched last year. If you want to hear more about the status and the mission itself, please come to my talk on Thursday morning, I think it is, yeah. So just to give you a little bit of background, since you won't hear my talk till Thursday, NISAR is a joint mission with the Indian Space Research Organization. It is both L-band and S-band. The L-band observations are made globally over all land and ice-covered surfaces, ascending and descending. It's sort of a similar pattern to what Sentinel is doing with the global coverage. And the S-band is acquired regionally around India, surrounding countries, as well as Antarctica, Greenland, and a number of other sites around the world. So this is a 240-kilometer swath, 12-day repeat mission, similar to Sentinel, but in a very different orbit, with a number of different modes: polarimetric, interferometric, repeat pass, and full swath, full resolution over all the targets. It's a 3-year nominal mission, but ISRO is going to operate it for a minimum of 5 years from their perspective, and the system, I can report to you now, is quite healthy so far. It's been a year, almost a year since launch, and everything is looking good in terms of resources and capabilities. So if we're lucky, knock on wood, it will last much longer than 5 years. It's been designed specifically for good pointing control and good orbit control so that we can do reliable interferometry. And you'll hear more about the details of that on Thursday if you come to my talk. And of course, it has a very large duty cycle in order to cover the Earth as it's covering it. And we look uniquely to the left side of our velocity vector which gives us exquisite coverage of Antarctica at the expense of polar coverage in the north, which is covered very well by many other missions. All right, so now I'm going to talk about urgent response, and since my eyes are no good, I'm going to have to look back this way, so apologize for that. Yeah, so one of the requirements that we created in the early days of NISAR at the encouragement of our other government agencies that use SAR data was to create some sort of a capability for urgent response. You may or may not know that NASA is not part of the international charter because all NASA data has always been free and open, and so they didn't actually feel a need for joining the international charter. But there's still a desire for coordination and contribution to urgent response. So we have a capability built into it that allows us to be able to acquire data at request quickly, as well as to create faster products that can be given to users in the event of an urgent response. And something like 7% of our processing capacity is dedicated to the ability to process data more quickly, get it out to users within around 6 hours. So this is supported, this urgent response capability is supported by this so-called smart tasking tool, which is a way to automate the process of acquiring urgent response requests, as well as provide a means for manual contribution by users to that request. So as you can see, there's an automated capability which allows various agencies to put in their own programmatic means for deciding when a disaster or an urgent response request is needed. That gets fed directly into the tool, which then schedules an urgent response. There's also a manual submission interface. It's basically a web interface, which is at the moment highly regulated to just a few users. I'll talk about that in a minute, but it eventually, I believe, will be opened up to a broader community of people who could make these requests. So the idea is that we respond to these kinds of disasters: earthquakes, fires, floods, volcanoes, hurricanes, and that kind of thing. A request comes in either automatically or from a user, and it is then goes into this smart tasking tool, is dispositioned by the tool, goes into the ground system, and then gets scheduled by the operations team. If it's actually a request that has to go to the satellite for additional acquisition or a change in mode, then that has a certain timeline. And if it's simply give priority to getting these data out to the community faster, that has a different mechanism. But this is all managed through this process. And then eventually whatever happens here in the planning section gets filtered back to the user so they can understand what's going on. So these are the guidelines that we've developed over the years. We are a science mission. NISAR is a science mission, not an operational mission. So there's always a tension between servicing all the different needs that would potentially perturb our science observation plan versus just doing the science. So these are the guidelines that have been carefully negotiated. We have a reference observation plan that is for the science, covering all the land and all the ice in particular modes in a very regular basis over the life of the mission. And that is of highest priority for the mission. We don't want urgent response unless, of course, the president or somebody like that says you must make this observation. We don't want these kinds of requests perturbing the observation plan. As a result, one of the key decisions is we don't repoint the satellite. We don't turn its roll angle at all, or point it forward or back, or move it from left to right in order to be able to service these requests. We just either turn on the system if it's not turned on already, or we change the mode if we need to change the mode. And as you can see, the second bullet is no change in instrument mode from the baseline plan. That is a true statement for the guidelines, but as I said, you never know. If there's an urgent enough request to change the mode, we may consider doing that. But the idea is that since we are repeating everything, all land and ice, every 12 days, ascending and descending, changing the mode may actually be detrimental to having a continuity in the time series. So that's the idea, is just keep preserving the baseline plan, but maybe allow the data to be downlinked faster. So the key thing here is the expedited processing. When we collect the data over land and ice, since we're doing it all the time, the primary thing that we are doing is expediting the production of a product and distribution of that product. We do have the ability to update the observation plan within a 24-hour turnaround time. It's the way they do the planning. Generally, it's a 2-week plan that gets updated or uplinked, and then they do have the ability to punch in a command within that 2-week window. They don't like to do it. It's a lot of effort. It's much easier just to expedite the processing, but we have the capability. We've demonstrated this in the past, and for truly urgent responses that need it, we will punch in these observations. And one of the key things here is that we cannot really interfere with our with our ground station schedule. The schedule itself for downlinking is also built with 2 weeks in advance, and trying to reconfigure the entire system for downlinking data to a new station is just too burdensome. So we're not planning to do that because they're finalized a week before. Okay, and then the last is we will be accepting manual requests soon. At the moment, we're just doing the automated requests. So you will see at my talk on Friday a little more detail about this, and there'll be another talk by Haresh Fatahi on the overall products and production flow and algorithms for NISAR on Thursday. But this is just a summary of our products that are available. All of these are freely and openly available, except for maybe the Level 0As. Level 0B, raw, unprocessed SAR data will be available. The range Doppler SLC, which many of you are familiar with, will also be available. Then in the geocoded domain, we have a geocoded SLC, a geocoded covariance product, an offset field, and a unwrapped interferogram field for nearest neighbor interferograms. These products are what are mostly being targeted for urgent response. The entire suite here, including these range Doppler, offset, and interferogram products, will be available also, but these will be the ones that are processed for urgent response. You can read more about them in our handbook, which is published on our NISAR website, and there's also a product description document that's been published as well. Okay, so because we rely on orbits that have been reconstructed and pointing that's been reconstruction to get our precise products, there's a certain lag. There's also a global ionospheric model that has to be computed that goes into the geolocation corrections for our product. These things all take time to create. And so for the urgent response products, which need to be distributed as soon as possible, we won't have the final orbits, we will not have the final pointing, and we won't have the atmospheric corrections that we typically apply and supply with our products. So these are the nominal products. We use the medium orbit, which is it's actually within a few centimeters of our very final orbit, which is produced weeks later. Within 3 days, we can get this medium orbit, which we use for all our processing. We use a precise radar pointing for our nominal product. We do apply a geolocation correction using a global ionospheric model that we have at JPL, and we also calculate a tropospheric correction from the ECMWF weather model. And these things are available to the public, but usually with a 2 or 3 day delay from the acquisition. For the urgent response products, you can see we have to use the forecasted orbit to get it out quickly, the forecasted pointing. We don't apply these corrections or compute the corrections. And it's also available through the DAC, but much faster than the normal products. So the automated urgent response requests are done through a feed. This smart tasking tool accepts the feed and creates an urgent response request according to various thresholds that are triggered. I'll talk about these thresholds in a minute. And these are updated. The thresholds might be updated either higher or lower depending on the frequency of requests and whether we can actually service them all or not. And this is coordinated with the applications team and our disasters program manager at headquarters. And at the moment, we have 2 automated feeds from the USGS, one for volcanoes and one for earthquakes. So here is the pager, USGS pager request levels, the different alert levels, red, orange, yellow, and green. And these are the criteria for those different levels. The urgent response trigger is triggered for NISAR if any of these particular ones are true. If there's a pager alert that's red or orange, if it's yellow and it's in the US or India, sorry, it's a little US, India centric, and then an earthquake in the US or India that's greater than magnitude 7 and less than 50 kilometers deep. Some of these criteria may not be satisfied in this case, but we trigger that anyway. And then we have a definition of what's in the US and what's in India defined here. So it's very well structured and may be adaptable to the rest of the world when it comes to these US and India situations. I have like 4 minutes left, 2 minutes left, okay. Yeah, so this is an example of one of the earthquakes that we had in 2025. Expedited processing was given. 3 events were submitted automatically because they all occurred within the same period of time in the same region. The urgent response tasking tool sort of accumulates those and then puts them into one single request. We also have the same kind of thing for volcanoes. You can see here the smart tasking tool uses the volcano notification services, a number of different codes, and you can see these are the organizations that issue these codes. The manual request system is also done through the smart tasking tool. At the moment, there's 33 individuals from these agencies who have access to it. If you are not one of those people and you want access to put in a request, I suggest you figure out who they are and whisper in their ear, and they might want to do it. I think this system, once it becomes operational, will really open up when we start releasing the data, and we'll find the right balance for international contributions. You can get the data through the DAC. I think I mentioned that earlier. This is the search location. There's a beautiful interface that ASF has put together through Vertex, and there's also an API. And these are searchable by looking for urgent response eventually. At the moment, we don't have any products there. We are about to go public with the data in about a month. And once that happens, then these products will start showing up in the DAC available to you. And you'll note these as being different from the standard products. They will have a UR in the file name, this very short file name that we have for our files. Has UR here towards the beginning, as opposed to PR, which is a production file. And I'll just stop there. This was an earthquake that happened just a little while ago. It turned out that the UR event was not triggered because there was a little bug in the smart tasking tool and some file name was too long or something like that, like I was mentioned back here, these huge file names. So it didn't work in that case, but it will work in the future. Thank you very much.
Thank you, Paul, for your clear presentation. There's time for one question. Is there a question from the audience? Otherwise, I take the opportunity. You showed very nicely the thresholds that you set for volcanoes and earthquakes. Are you also considering to set up a similar system for other hazards in the
I think
future?
floods is the most obvious one that is likely next on the list. I don't know if there is a feed for floods that's available globally, but yeah, I think there will be other hazards that are triggered at some point. I don't know what the plan is. Let's get through the first year of operations with urgent response, and then we'll see how it goes.
Okay, thank you.
Thank you.
Thank you, Paul.
Thank you, Paul. So let's move to the next presentation. Simon van Diepen. Sorry if the pronunciation is not good.
Close enough.
Good. Thank you. Start, please.
Thank you for your. So I want to talk today about what I've been doing during my PhD project, which is called the Dynamic Digital Elevation Model. And the main question I want to show here is, can we look into the future using INSAR? So currently our INSAR products look like, well, like this. This is the EGMS. You're all very familiar with that. And it describes and shows these time series of observations over time as these red dots. Once you click on one of our nice colored dots on the background map. And these are all approximated with like the same steady state model for all points, in this case, a linear model. But for some points, that doesn't work. So for example, I picked one here that seems to have more of a periodic signal behind it. And there's also a second question, like, should we even show these observations to begin with? Because they can be very noisy, and that might also be interpretable as actual signal instead of just noise. So to skip straight through the end, this is what I'm proposing instead, the dynamic digital elevation model approach, where we distribute a model instead of the actual observations. So that would look kind of like a table like this, where we have points with possibly unique models. Then the parameters within those models, their variances, covariances, and possibly also different quality metrics, and just a list of which models can be used. And from that, you can recreate the actual functional models, which can be, well, broadcast back into the past or possibly into the future. You see here not a linear model or an accelerating model. This is actually a very specific model that I am going to talk about in a minute, which is dedicated to the area I am applying this to, which is this region, the green heart of the Netherlands. This is peatlands, which all look like these nice rectangular green grass fields. And peat is organic, so once you expose it to air, it will start to oxidate and basically vanish, so subsidence. This area is over 2,000 square kilometers large, and we have been draining this for centuries now. So, but this is also why the Netherlands is mostly below sea level, because all of these fields have just been subsiding like that. These fields are also quite nice in the sense that, well, they are averaging units. Instead of just nice grid cells, we can actually just use the rectangles as delineated by those canals. So if we want to create a dynamic digital elevation model from this region, we need data. So let's start with elevation. This is a digital elevation model of part of the region. And you can already see this is below sea level. So the bluish, medium bluish part is about 2.5 meters below sea level. The dark blue part in the top left, 4.5 meters. And for each of these parcels that we just have, we can get an average elevation, well, at one specific epoch. And because the elevation is so important in the Netherlands, we don't have one of these, we have multiple. So we have a second one, and then we have a second elevation at a different epoch, so we can just draw a line through it. Actually, we can't do this because there is a bias in each of these products that is unknown. So when creating these products for elevation, it's less important that it is like at the millimeter level, so plus minus 5 centimeters is fine. But that means that any of these lines is also possible. So which one is it? Based on just airborne laser scanning alone, we don't know. So we need something else. Benchmarks. These are part of the Amsterdam Ordnance Datum, which is our national leveling system. And very specific benchmarks are located in buildings, which we can also see from airborne laser scanning. So here on the left, you see the building from airborne laser scanning, where we can estimate the ridge line, the red line on the top of the roof. And on the right is the same building, but then with that benchmark. And from both, we can see how they are, well, moving, subsiding, or uplift, doesn't matter. We have a lot of those benchmarks. So all the sand-colored points, you cannot even see they are points because there's so many of them. All of them indicate one of these benchmarks. So in our area of interest, which is in the black circle, we have thousands of them, of which about 400 are useful. But how do they actually move? Because we also have an elevation time series from that. And same as with INSAR, these also have a reference point or a reference benchmark. And those are postulated to be stable. Question is, are they? So they are actually just special ones, special benchmarks that are part of that green dots you see, which are underground benchmarks. And they are all assumed to be stable, but we know they aren't. We know they move with respect to one another. So can we actually check if these reference benchmarks, which we assume to be stable, are stable? We can, using yet another technique, another collocation, gravimetry, absolute gravimetry stations. We have 5 of them in the Netherlands. And by taking the closest benchmark, once again, we can see what the reference benchmarks are actually doing. And we find, so these gravimetry stations are observing gravity at 10 to the minus 10 meter per second squared. And with that, it is sufficient to observe velocities of the order of 0.1 millimeter per year. And that's also what we find. We find these reference benchmarks are moving upwards at about 0.15 millimeters per year, plus or minus 0.12. So that number raises 2 questions. One, is it even relevant? Because it sounds so tiny. But if you propagate that, you actually see that current elevations would be biased by about 1 centimeter in the east, or in the west, and about 2.5 centimeters in the east. And the second question is it significant? Well, you can debate about that, but there's also no reason to say it is 0 in the first place. So we decided to use these results anyways. Just going back, why were we even doing this? We wanted to align these 2 DEMs. So now we have 400 buildings with benchmarks, of which we know the time series, which are now given with respect to the absolute gravimetry stations. And with all of that, we can estimate the bias between these 2 campaigns. So then we can actually draw this line. You saw the dot moved up a little there. And in fact, we don't just have 2. We have a 3rd one and a 4th one. And even back in the day, before airborne laser scanning was a thing, we spent about 50 years going through the entire country with leveling rods. So we have a 5th DEM there as well. Now, this does not look like that model I showed you before. This does not look like this. It's just a linear model because all these samples are, well, made every few years. So we cannot see a sub-annual signal with that. So this is where INSAR comes in. We need more dense observations. You can see here that in this example plot where we actually have ground truth from an extensometer, the annual signal is about 10 centimeters. That's going down in summer and going up in winter again. And we need to see that from INSAR. And we can actually do that. So this is on one of those parcels, the INSAR results. There's a couple of interesting things here. So first of all, you see that there's gaps, and during those gaps, the daisy chain coherence is so low that we don't have any information left. We're talking less than 0.1 in 6 days. So there's no information content there, so we just discard those observations altogether. Which leaves, well, kind of groups of disconnected points. And we need to reconnect those using, well, the whole procedure is described in the paper linked over there. That by taking nearby parcels that we expect move similarly, we can kind of bridge these gaps. And the second thing is this model. This is not just any periodic model. You can see, for example, in 2018, the periodic signal is much deeper than in 2019. 2018 in the Netherlands was a very, very dry year. So we need some sort of environmental driver here. That is what we call SPAMS, which is a model that mimics the water table, but without actually measuring the water table. So it's driven by precipitation, which is raising the water level, and evapotranspiration, which is draining it. And the soil, the surface level, reacts in a very similar way. And yet again, we're left with the reference point, which has an unknown motion. So we need, again, one final 5th technique, GNSS. This is an integrated geodetic reference station, of which we have over 30 in the Netherlands by now. And it is an ideal reference point for INSAR because it has these nice big corner reflectors with a GNSS antenna on top. So we know exactly what they're doing. And there's also opportunities to connect with different techniques here even. So the horizontal plate is visible in airborne laser scanning data. And there's benchmarks for leveling, for gravimetry, and some other techniques as well. So finally, we can actually connect everything. We have everything into the same datum, and we can actually estimate models. And we do that at the regional scale, over 2,000 square kilometers, at the parcel level. So there's about 80,000 parcels here, which all have their unique model with their unique individual parameters that, well, so each one has something that looks like this. With the SPAMS model causing the jiggles, the periodic signal over here. And you can also see at the regional scales that there are definitely subsidence hotspots here as well, specifically in the northern part near Amsterdam. And in the central part, there's a lot of red, very fast subsidence going on. So to conclude, using the DDEM methodology, we can evaluate elevations of these parcels at any epoch. And because it is a functional model, we can go back in time as far as we want, given that well, the motion driver should still be the same. We can also look into the future, and in this case, we would need climate models because we need precipitation and evapotranspiration. But it is possible, we can do that. And by using these 5 different geodetic techniques, we allow for better elevation and elevation change estimation than using just individual techniques. But we are still dependent on opportunistic collocation. That's the buildings with the benchmarks in them. And we can do this at regional scales to estimate vertical dynamics of, well, basically 5% of the entire country at once. Thank you for your attention.
Thank you. Thank you for the presentation. Any question?
Yeah, thank you for your talk. I really like the idea there that you build it around, let's say, a joint model, joint datum. So the results you show here, I guess, were based on Sentinel, like the first maps you put up there. So my question is, based on this framework, can you also then start now to integrate the other sensors more efficiently? Even maybe, I mean, you rely on your datum and your reference point, but since you kind of conditioned the model, even sensors that have measured like ERS or others back in the past there, right? You could connect them still locally and via the model, I believe. So I think you could do the extension, or what is your take on that?
Yeah, so I believe the main question is, can we use other sensors here as well? And yes, we could. In this, for these maps, I have only used Sentinel data indeed, but we could go back to ERS, to RadarSat, to other sensors that were there in the past. You would need to figure out the reference point issue, because at that point we did not have for like the data really far in the past, we did not have the IGRS stations installed yet.
Exactly, but since you, let's say you kind of conditioned your datum now with Sentinel-1 and having a station in there, at least location-wise, you could start to connect the dots at least in some ways that you do the extension and align it based on the model, I believe.
Sure, yeah, you can create other reference points that you assume to be moving based on the Sentinel data. And project that back into the past. You could definitely include more data sources than what I have done here.
Any other question?
Thank you, Simon. I have a question on the interpretation of the reference benchmarks. So you were saying that the leveling benchmarks are moving up. So I was wondering, do you have any explanation of that?
Yes, so indeed I stated that those orange benchmarks are moving, well, slightly upwards. And in fact, you kind of can see that effect here as well. There's kind of a tilt going on in the entire country. And that tilt is due to loading from the North Sea having filled up, well, about 8,000 years ago, I believe now. Which is still kind of rearranging the crust around the Netherlands, pushing the coastal areas down slightly, and kind of creating a tilt around the central part of the Netherlands.
Yeah, another question there. And then we move to the next presentation.
Thank you for interesting presentation. My question is about the frequency of measurements of these benchmarks. How often these leveling benchmarks or gravity points they are measured?
So our gravity benchmarks are observed yearly. Every year, so around the summer, there's a campaign visiting all of the stations. Leveling it depends a bit on where exactly you are, but the second order benchmarks are generally visited every 5 to 10 years 5 years in areas with expected subsidence, like the Groningen gas fields, 10 years in other regions where less motion is expected. And the first order benchmarks, which are the green ones, they are visited approximately every 20 to 25 years as like a national leveling campaign. But they are used to tie the second order network to during those smaller campaigns as well.
Okay, thank you, Simon, for your answers. We go to the next presentation, which will be given by Alessio Morea.
Good morning, everyone. I'm Alessio Morea, and I'm here to represent a collaboration between BioOpen, Delta Phi Remote Sensing, Delft University of Technology, and the Università di Alicante for the project Copernicus SAR Analysis Ready Data, which was founded by ESA. In this project, the main objective was to develop advanced processor for a new generation of SAR products. And while these products will be easy to use for the end user, they will still keep state-of-the-art scientific quality. After a first phase where we compared the different type of products, we chosen the co-registered single look complex, or CSLC, which will be aligned on a common radar grid. It will preserve full measurement fidelity. We will both perform model-based and data-driven co-registration. Then, the second product is the geocoded multi-looked phase, which will be given on a standard UTM grid, usually with a 50-meter posting, in order to reduce speckle and improve coherence. And also, since the algorithm is really efficient, there could be a regular update with each new acquisition. We have chosen these products because they are the foundation for many other ARDs. For example, starting from the CSLC, one can easily compute the phase and coherence with respect to two different images in the stack, or compute the temporal despeckling and amplitude dispersion, or something more related to Earth observation tasks. For example, change detection, or soil moisture, or persistent scatters. So, since we have to deal with a massive amount of data, mainly the Sentinel-1 and Roselle missions, we are using all modern technologies, and our processor will be implemented in a native Python ecosystem. Our main libraries will be X-Array and Dask in order to have perform parallel computation and be able to use chunked and lazy datasets. And our library to store data will be ZAR, so a cloud-optimized storage. Our processor will be modular, so it is really easy to modify it and add new sensor, and we have an open source commitment. So at the end of the project, the complete code will be released as open source software, and it could be used to have transparent scientific validation, for example. We will validate the products with sites all around the world, for example, Campo Flegrei in Italy, or Surrout Base in Australia, where there are a lot of corner reflectors. And we will use different metrics to validate the products. For example, artificial reflectors, where we compute the co-registration accuracy, the resolution of the azimuth in range and azimuth pixel, the SLR and PSLR, or for example, exploit the phase continuity and residual azimuth shift in correspondence of burst overlaps. So for the CSLC product, since Sentinel-1 and Roselle share the same orbit, we decided to propose a unified radar reference grid where we will project both bursts of the missions. So this grid is constructed simply from a single shared points, so an anchor node, and we define the grid intervals in order to preserve the finest resolution for each sensor while keeping an integer rate constraint between the two bursts. the two missions, sorry. The grid size will be obtained simply starting from the expected footprint of the burst and the reference orbit of this particular track that we are computing, and the application of zero Doppler equations. So first we will perform a model-based co-registration where we use DEM, orbital data, and timing correction. This process will be applied independently on each burst. And while this is generally sufficient for C-band, for example, here we show a phase mosaic over Atacama and its coherence. Usually in C-band, there are small residual phase discontinuities that can be easily recovered through SD. For L-band, this is not enough, since the signal offset are even 18 times larger than C-band. So it's required to perform data-driven co-registration in order to achieve sub-pixel accuracy. This is an extreme example on Sentinel-1 data over Taiwan in 2016, where with only model-based co-registration, it is clear there are phase discontinuities between burst and residual phase ramp. So in the processor, we implemented the image matching and ESD technique in order to refine the range azimuth pixel alignment. And as we can see, phase discontinuities have been removed. Also, we will implement the split spectrum technique coupled with image matching in order to compute the ionospheric phase screen and correct it. Here, I loaded the main variables of our CSLC product in a simple X-array dataset. As you can see, we have the dimension will be the polarization, the acquisition date, and the azimuth and slant range time. And the main variables will be the CSLC, so the actual co-registered measurements. And to be completely transparent, we also report the phases that have been previously computed and removed. So the phase model, so the model-based phase correction, the ionospheric phase screen, the tropospheric phase delay, and the phase contribution due to tides and system corrections. Once one has loaded this dataset into memory, or lazily, it is really easy to, for example, select the reference image from the stack of all our images, and with just some 2 lines of code, compute first the product between all the images in the stack and the reference, the conjugated of the reference image, and then a multi-looked interphogram, and with one additional line, extract the phase from the result. And here we show an example over Milan. Or one could even compute a simple geometric mean over a stack of co-registered images to perform temporal despeckling. Here we did it for more than 200 images. So the CLC will be robustly validated, and we will ensure that all the figures of merit, for example, the delta azimuth and delta range, localization error, and many more, will be consistent with the original input level 1 SLC product reported in the Sentinel-1 annual performance report. Instead, the second product is the GMLP, which is a completely new product that will simplify interferometric processing for both single interferometric phase and full time series. And when one initializes the stack, we define a current reference image that will get updated with new acquisition date, with each new acquisition in the stack. And the update will simply be a linear combination of our previous current reference image with the new image in the stack. This will enable us to provide the consistent multi-looked interferometric phase, where we also introduced a drift correction mechanism in order to prevent a drift during the years. Since we are dealing with multi-looked quantities, there will be a massive data reduction with respect to CSLC data. And the update will be really fast in correspondence of each new acquisition. It's also important to notice that we don't require any computation of full covariance matrices. Also, we will contain some coherence layer to assist further processing. And here, in this paper by Francesco De Zan, one can find additional information about this. So here we show, just as an example, the intermediate product of our processor, and it's geocoded, which is the image, which has been geocoded with the sync interpolator. This was taken over Naples using the SACOM satellite, and it was over a 5-year acquisition stack. The long-term coherence is one of the quality layers that accompanies the phase layers. This is computed simply as the coherence between our current reference image and all the images that have been previously selected as stable reference images. And it provides a clear indication of how stable it is, our current reference. Then here I loaded the main variables as an XRA dataset. Apart from the phase and the long-term coherence, which I already talked about, there is also the short-term coherence, which is just the coherence between the current reference image and the newest image in the stack of data. Here we loaded them directly in GIS. Below we show an example of the short-term coherence, and on the right, the interferograms that are actually saved in the product. So 2 5-year interferograms. And then only using QGIS band math, it's possible to compute their phase difference and obtain a 16-day interferogram. So we have also some metrics for the GMLP validation. For example, here we computed the average and standard deviation displacement during 5 years. And we compared our processor, that here is reported as CMLC, with respect to our processor without the drift correction mechanism, signed these are NDC, and the MEI algorithm. So we can see that the MEI SMLP predict really similar results without, and even if the CMLC is cheaper on computation. So in conclusion, why will simplify processing while maintaining rigorous information quality? Our products will be the CSLC that will be given at full resolution, and the GMLP, which is an innovative RD product, and it will inherit all CSC corrections. It will be used for both the Sentinel-1 and Roselle missions, and the prototype processor will leverage cloud-native technologies and will be completely open source. That's all.
Thank you very much. There's time for questions.
Hi, thanks for the talk. It's really cool to see these kind of analysis-ready products being developed for Sentinel-1. My question is to you about the coherence products that you were mentioning. You mentioned that the phase stays stable, so I'm wondering at what stage do you calculate the multi-look coherence essentially from your geocoded product? Do you first calculate the coherence in radar coordinates and then geocode it, or do you use the...
Yeah, we do everything in radar geometry and just geocode it with the sync interpolator.
Okay, thank you.
Other questions? There's one all the way down here.
I have 2 questions. So you said that for the co-registration, you are doing not only the geometry, but also you are doing data-driven estimations. So what do you think of operationalizing that? Do you think it's doable? aren't you afraid that there will be a lot of artifacts in doing so for the Sentinel-1, especially for the azimuth direction?
Yeah, I hope so that it could be made operational. Also in the data-driven co-registration, we will use the current reference image that I was talking about. So we hope that with each new acquisition in the stack, we continue to keep trace of important quantities for the data-driven co-registration. Okay.
All right, and my second question is this about developing the processor, or ESA is committed to make these products actually?
Can you repeat it?
Is your presentation only about the processor, or ESA is committed to make the products using this processor?
No, at the moment it's just a prototype. So
okay.
There are no...
Thanks.
Anyway, Nuno Miranda in the presentation of yesterday mentioned that in 2027, some ARD products will be provided probably for Sentinel-1 and Roselle, of course, when the mission will be launched. Anyway, it's not yet fully decided by ESA, but probably...
No,
What?
the processor is a little bit different. We will do mainly model-based co-registration, no data-driven for Sentinel-1.
Are there more questions? I have one, so you can still think about another question if you want. You were showing that you're going to use a common grid,
yeah,
for the Sentinel-1 data and the Roselle data, especially regarding the Sentinel-1 data. What's the effect on point scatterers regarding this extra resampling step?
Well, at the end, in model-based co-registration, you don't actually need the information quality in the reference image, no? You can just always reproject it onto a reference grid. There should be no problem.
Yeah, what I'm thinking of is that, of course, the image is acquired in its original SLC grid, and you're resampling it to the other grid. So.
Yeah, the original image is resampled onto the common reference radar grid. But it's just a mathematical computation, this grid. There isn't... We also keep the spacing similar to what it would be in Sentinel-1, so there should be no artifacts, I think.
Okay, thank you. There's one more question there, and after that we move to the next speaker.
Thank you very much for your talk. I kind of re-echo the idea of bringing this and operationalizing that. I think Harish is also speaking from experience for the CSLC product from Sentinel-1 created over North America. We explicitly down-selected the data-driven approach as not very viable to operationalize. So I would think Sentinel-1C is also not consistent acquiring data outside of Europe, where you start having challenges to do the data-driven approaches. So when I saw you embed the ionosphere correction in the CSLC, I assume that also comes with the assumption of making an interferometric pairing network and then re-inverting that with respect to a reference scene. So it's also not yet absolute in terms of the phase and has potential challenges for accumulating noise. So I would recommend potentially to also look at the JPL side and see what the lessons learned was from the ATBDs and also from the review panel which ESA was participating in.
Okay, thank you. I didn't get the question, it was just a comment, okay.
Okay, so thank you very much, Alessio, for your presentation. Let's move to the next presentation, Franz Meyer.
Yes, so thank you for sort of the setup for this presentation on CIOS application-ready data products. Who in the audience has heard of the CIOS ARD effort? Paul doesn't count. Okay, yeah, there's a few in the room, but they're not enough to invalidate my talk entirely, so I'm going to go through the talk anyway. So CIOS, the application-ready data group, is a consortium of a lot of international organizations that are shown here on the slide. I'm giving this presentation just on behalf of many people that have worked on CIOS ARD for a while. The goal of CIOS ARD is sort of multifold. One of them is to basically increase the uptake of SAR datasets by non-experts. So the idea is to provide specifications for higher level data products so that data providers in the future know what these data products should look like, what we mean when we say like an RTC product or a normalized radar cross-section product, what an interferogram product should look like, what information it needs to contain in order to be viable for downstream applications. But it also, by providing specifications, it also is supposed to create some interoperability where data product provided by one producer for one data set and one source can be used together with data sets provided from a different producer. So there are broad goals behind CIOS ARD, and CIOS ARD also developed specifications not just for SAR data sets, but also for optical data sets. But today I'm going to focus on the SAR work that has been done by the team. And so within CIOS ARD, there have been a number of specifications made for different SAR-derived products that are listed here, and I'm going to go through a little bit in this talk. One of them is an interferometric radar product, which is probably most interesting to this community, but there are also normalized radar cross-section, polarimetric datasets specific for the ocean communities, as well as a geocoded SOC product specification that was developed. If you're interested in what the team is doing, please follow this QR code. It gets you to the website with all the information that I will be providing you today. If you are a data provider and want to be engaged in this effort too, please send me an email or anybody on the team, the CIOS ARD team, to join this effort. So the goal is to develop product family specifications for a variety of different products and then provide guidances to data providers regarding these specifications that are listed here. So what is the radiometric requirements in order to meet the specifications? What are recommended geometric corrections that should be applied? There is a set of general metadata that are recommended for each data product, as well as per pixel metadata that are recommended in order to meet the requirements or sort of qualify as a CIOS ARD product. There are two levels of requirements for each data product. One of them is a threshold requirement, which is needed in order to meet the requirement. And there are goal requirements, additional data layers that can be provided to make the product you provide as impactful as possible. The metadata specifications are supposed to be accompanying the radar data sets. There is a need for consistent nomenclature of parameters between the main radar data sets and the metadata requirements. Currently, the specs are written in a form of an XML data set, but there's no specified data format that is recommended by the CIOS ARD team. So the data formats right now are not mandatory. And so the overall product family specifications, they contain three components. There's information about the radar measurements specifically, sort of how does the radar data set need to be processed in order to comply with the specifications. There's sets of per pixel metadata, such as the ones that are shown here on the slide. These are specific for the normalized radar cross-section product. where you see incidence angle information, noise flow information, conversion factors that are provided, and data masks that are required or recommended for this kind of product. And then the third component are these general metadata descriptions that are really allowing to have traceability of all of the input data that is used for a specific data set. So using these overall guidelines, the team has developed a set of SARS-specific product family specifications. So the first one is the normalized radar backscatter product, which basically is a RTC type, a radiometric terrain corrected type data product. The radar measurements are specified to be geometrically corrected for topography and also contain a radiometric correction for slopes. And the data sets are supposed to be provided in a gamma zero projection. So you see an example here for an ALOS-2 data set where you see the HH and the HV gamma zero product provided for a COS ARD compliant product. There's a set of per pixel metadata sets that are required. One of them is a local incidence angle map. There is mask images that mask out invalid pixels, as well as traceability for the acquisition ID so that everybody knows which original SAR data sets this product was derived from. There are optional additional metadata requirements, such as a conversion layer that allows you to go from a from a gamma zero to a sigma zero projection for communities that are more familiar and are more accustomed to a sigma zero data set. So examples are shown here for this particular product. I'm going to show you a link at the very end, again, to a place where you can actually downlink the specific specification. A second one is a polarimetric specification that you can sort of consider as an expansion or extension of the NRB specification, but adding in additional polarimetric information for data sets that provide multiple polarizations. Because it's an extension to the NRB specification, most of the general metadata and the per pixel metadata is very similar to what I showed you on the previous slide. But in terms of the radar data itself, there's two polarimetric information layers that are required for this particular specification. One of them is a polarimetric decomposition layer, but the data provider can choose which particular decomposition they want to provide. And then there is a polarimetric covariance matrix information that is also required for this particular product. And so an example is shown here for RADARSAT-2 on the left-hand side, where you see a decomposition on top and then the individual matrix elements on the bottom. And so they are useful for a variety of polarimetric applications. The covariance matrix also for pol-insert applications. There is a product specifically for the ocean community. So that's an ocean radar backscatter product that's akin to the normalized radar backscatter over land, but here for the ocean community. The differences are that the ocean community doesn't do flattening based on topography, obviously, but uses a geoid layer for slope correction. And also the products are provided traditionally in sigma zero and not in gamma zero format. So here you see some examples on the right-hand side for gamma zero, sigma zero backscatter for VV and VH for a Sentinel-1 data product. What else to say here? So there's a land mask that is also required. So in this case, the valid pixel mask would mask out land pixels. Then going more toward the INSAR space, one specification that was developed is one for geocoded SOCs. So this is a fully complex data format in a geocoded space at the original sensor resolution that is there to enable and sort of shorten the path toward an INSAR and interferometric product. The idea is that the product is fully interferometrically viable. So the product should be aligned for a reference orbit or a reference geometry so that interferograms can be created by simple cross-multiplication of different layers. The idea is also that the topographic phase should be automatically compensated so that a interferogram would highlight deformation phase right away. So co-registered to interferograms to or co-registered enough for interferogram formation. And that leads me to the final product, which is a differential interferometry or an INSAR data product, which contains 3 different layers. One of them is the wrapped phase, one is the unwrapped phase, and the third is a coherence layer that are mandatory for this particular product. Those are also there to expand the user community for the folks that want to use INSAR but are not familiar with the INSAR processing workflows. In terms of the metadata and per pixel metadata layers, the mandatory layers are fairly small, as you see on the right-hand side, but on the goal layers, there's a variety of different layers that can be and should be included in a product like this. Some of the ones we heard earlier in this set of presentations, there is a look vector information so that data can be projected into sort of combined with geophysical models. There is atmospheric, ionospheric correction layers that are recommended, as well as simulated topographic phase information, etc. So in addition to providing specifications that help data providers provide data sets that are more interoperable, there's also an idea behind making these data sets more accessible and more discoverable. In a space where more and more these ARD products become available, there's going to be a larger set of providers and a more distributed set of archives where these data sets are located. So the CEOS team is also working on stack definitions and stack extensions that data providers can adopt so that their data sets are jointly discoverable and people can build discovery platforms on top of these archives. Also, the QR code here leads you to the GitHub page where the latest version of the stack extension is described. And so there's good community uptake for these specifications, and a growing number of data providers are now compliant or approved as compliant products. So a list is shown here. There's currently 13 different data products, NRB data, polarimetric data, and first INSAR data sets that are approved as CEOS ARD compliant, 9 different data providers and data from 6 different missions. And the list is constantly growing. There's currently a large set of data sets that are currently under review or in preparation. 14 different data products is listed here. This is sort of grabbed from the website yesterday. 6 different data providers and data from 12 different missions. So there's broad interest by the community to provide data sets that are CEOS ARD compliant. Again, the QR code gets you to the website, and on the website you find all of the lists of the current data products and the ones that are in development. Just at the very end, there's some additional specifications that are currently being looked at and considered. One of them is a multi-source NRB product, sort of a radiometrically corrected multi-source product, which could allow either for combinations of ascending and descending data to increase spatial coverage, or a product that uses multiple input data from multiple sensors to provide higher temporal resolutions. And the team is kind of thinking about how such products need to be traced and what kind of information needs to be available for these products. There are, the team is also thinking about very high resolution SAR data sets and its implications for NRB type data products. What requirements would we have for the associated DEM that is used for creating NRB products, and are these kinds of RTC corrections that we're applying here still viable for this very high resolution data set? Other two are co-located SLCs or CSLCs that would be very high quality co-registered, as well as geocoded multi-looked complex RTCs. The one that's already approved is or already out there is a full resolution SLC product, and currently the team is thinking about also a multi-looked SLC product. And lastly, so follow the team at the website. And again, if you're interested in playing a part in this team, if you're a provider that has data sets you want to get approved as ARD compliant, CEOS ARD compliant, please look at the website. Feel free to send me an email or talk to me separately in the break. Thank you very much.
Thank you for the presentation. So we have time for questions.
All right, thanks, Franz. If I understood correctly, you said that for GSLC, it should be radiometrically terrain corrected. Is that right?
That's what the current specification is saying. So that's probably not what NICER is currently doing, right?
Right. I mean,
Yes.
we didn't want to impose on the users necessarily go to GammaNet. A lot of people are still interested in SigmaNet, so that was the reason.
Yeah, so that's another reason to potentially engage and provide feedback to the team. These specifications can be updated, both from sort of a physical meaning and sort of community adoption perspective, but also from more a practical perspective. Many of them may contain lots of layers, per pixel layers, that the team would have thought would be useful for the community. But if you do global production, it may not be practical to produce all of these. So if you have these kinds of insights or input, please provide feedback to anybody that's on the team now, or also feel free to try to join the team and provide that feedback.
Or the opposite. I think CEOs should look at what we have done for NICER. We are producing 14 products at least, and many of them are analysis ready. So we have spent tons of times designing those products with you guys on science team and the project as well. So I think it could go the other way. And
exactly. Yep.
I have not had time to attend those meetings, but I have had multiple team members to attend semi-regularly, and I have felt the frustration that sometimes there has been resistance on metadata that did not make sense, and we were confident that it was not making sense. You mentioned some of them right now. So that's something maybe we can discuss more.
Yes, so correct. So there, I mean, it's been a dialogue, I think, in the development of these specifications, where sort of multiple parties have multiple opinions. But again, all of these specifications, feedback is always welcome, and people from various teams have been on the writing team for these specifications, but it's a difficult dialogue between members from different communities about what needs to be contained in these specifications. Right, but yeah, so feedback is always welcome as this team goes forward.
Thank you.
We have time for the last quick question.
Hey, just a quick question. What's the timeliness and review process like for getting certification for an ARD product?
So let's see, maybe Haresh knows this better than I. How long did it take for some of the products to get approved? So the initial review is, I think, regularly happening and reasonably quick, but there may be a back and forth between the provider and the team. So I'm not sure if I have a good number. Do you have a number in mind? 6-7 months. Yep. Yeah, so I think there's a learning process still happening on both sides. And I think the Opera approach is an example of how this can go both ways. I think the specifications in the end were slightly adjusted to accommodate practical considerations about data volumes, et cetera.
And then a follow-up question would be, is there any risk that the requirements can change? So let's say a product gets approved, but then sometime later there's some changes, then you have to resubmit and re-go through the approval process again?
Yes, so with the Opera case, there were some changes made to the requirement.
Okay, great, thanks so much, appreciate it.
Okay, I think we have to close this session. So thank you to everybody for participating, and we can go to lunch.
Hello, good afternoon. Thanks for coming. So not everybody's here after lunch yet, so still we need to take the agenda and try to start the session now in the afternoon. So here I have with me and myself, Jose Manuel. So we try to drive this afternoon session. So we want to invite Mattia Calegari for presenting a cloud-based solution for SentinelOne insert processing with OpenAO. Thanks, Mattia.
So thank you for the introduction. In this presentation, I will show the main outcome of ESA-funded project where we developed as a URAC research together with Vito Remote Sensing a cloud-based solution for processing SentinelOne INSAR with OpenAO inside the Copernicus data space ecosystem. Okay. Okay. So as we all know, SentinelOne insert processing requires the access to a quite large amount of data and also a significant computing resources. So before we started the project, the Copernicus data space ecosystem, the CDSC, already hosted basically all the Copernicus satellite data, including the SentinelOne single log complex data. On the other side, OpenAO is the API which provides the unified access and processing capability to the satellite data, to all the data stored on the Copernicus data space ecosystem. However, before we started the project, OpenAO still did not provide the possibility to access and process SLC SentinelOne data. And this was the main motivation of our project, that is then to bring the possibility for processing SLC data with OpenAO inside the CDSC. So from a user perspective, the OpenAO processes that we developed looks as any other OpenAO process, but inside this we implemented using CWL, a common workflow language, scalable workflow pipelines, which can call in an easy way different Docker container inside which we implemented the access to every single SentinelOne burst through the CDSC utility, the processing of SLC data using the Snap tools, and then provide the output as a stack catalog to be compliant with the cloud-based infrastructure, and also to be homogeneous with all the other output that OpenEO provide with the other satellite. So if we want to go a little bit more in detail, what is available for the user. So we start with a Python notebook, which can be executed in the CDSC Jupyter Lab, in which interactively the user is guided on the selection of the burst ID of interest based on the area of interest that the user can define. And then also this Python notebook can provide the generation of the graph, of the interferogram graph with the temporal baseline, the perpendicular baseline, for supporting the definition of the interferometric pair list for the generation of, for example, a time series of interferograms. So one defined this input, then the user can define the OpenEO graph for calling the processes that we implemented, that are mainly three. So one dedicated for the generation of geocoded coherence, the second for the generation of geocoded interferograms, wrapped and unwrapped, and the third, the simple generation of a co-registered stack of SLC in SAR geometry, which can be then used as input to any custom OpenEO processes for generating other products, and then also geocoded through a geocoding process that we implemented directly in OpenEO. As I mentioned before, then all the outputs are generated as a stack catalog. So we tested our processes by defining two different use cases. So the first is dedicated to the generation of a time series of coherence for land cover classification, and more specifically for the detection of glacier, with a specific focus on debris cover glacier detection. Here, this is a quite common application in the cryospheric domain, where we want to use the interferometric signal, and in particular the coherence, to detect the part of the glacier that is covered by debris. That is something that is difficult to detect using optical data only, simply because the debris that are covering the ice have a spectral signature that is very similar to the surrounding debris. With the SAR coherence instead, we exploit the fact that the debris that are covering the ice are affected by the continuous motion of the glacier, and therefore are characterized by a coherence values that is much lower than all the other debris, the surrounding debris that are not covering the glacier, and that are therefore more stable. The second use case instead is more focused on surface deformation monitoring through multitemporal interferometry. And here we did not implement a workflow inside OpenEO, but what we wanted to test was if the time series of interferograms that we generate with OpenEO can be easily used as input to an external software for multitemporal interferometry analysis. In this specific use case, we selected MinPy as the external tool that we wanted to test. So coming back to the first use case, we considered one summer, the summer 2023, so all the Sentinel-1 acquisition from the 1st of July to the end of September 2023, and we consider all the Sentinel-1 bursts that are covering all the glacier of South Tyrol, which is a region in the eastern Italian Alps, close to the border with Austria. In this case, we have 25 bursts that are covering our glacier, acquired in 5 different orbits, 3 ascending and 2 descending. We generated all the 12 days baseline coherence for a total of more or less 190 pairs. So this is the OpenEO graph that we used for the generation of all these time series. And here you can see the actual code that we used for the generation of the graph, calling generating all the time series of coherence. And I show it here just to have a feeling of the level of abstraction that we could have achieved with this. So you can see that simply the user can define the process ID and then specifying the input parameter like temporal extent, temporal baseline, burst ID, and so on. Then in this case, we also apply another OpenEO process, which is the multitemporal mosaic. In this way, we reduce from the multitemporal time series of coherence, and we extract just the maximum temporal coherence, which is the most relevant feature for the detection of the glacier in this case. Here in the slide is the resulting spatial mosaic of this multitemporal mosaic of the coherence, and this is the actual input feature that we used for the classification of our glacier. We use a very simple classification approach that is a threshold-based classification, but still you can see here with this example the reliability of the classification. So basically here we have in the blue dashed line is the glacier inventory of around 30 years ago, which define the area of interest where we want to apply the classification, with the realistic hypothesis that the glacier did not expand with respect to the almost 30 years ago. And then in green we have the glacier outline resulting from the classification of our coherence, and in red is the reference glacier inventory, which was realized the same year with very high resolution orthophotos, airborne orthophotos, and LiDAR acquisition. Here I also present an optical image covering this area, just to give you the idea of the importance of using the coherence in this case. As you can see here, all this part of the glacier is covered by debris. From the optical image, basically we cannot distinguish that these debris are covering the glacier and these debris are not covering the glacier, because the spectral signature is very similar. Instead, in the coherence, the signal is very evident, because we have this decorrelation due to the glacier motion. Coming then to the second use case, the multitemporal interferometric analysis. Here again, we simply wanted to test if our time series of interferograms can be easily ingested in MinPy, in this case, for multitemporal interferometric analysis. So for this reason, we selected a very famous data set regarding the Ridgecrest earthquake in California in 2019, simply because this is also reported in the MinPy tutorial, and there we also have the results available in the MinPy tutorial, resulting from the analysis done with the time series of interferograms generated with another tool, of course, and not with our OpenEO processes, but in this case was generated with the Alaska facilities. So this just to have a reference to compare then the result we can achieve using our interferograms. So starting with our Python notebook executed in CDSC, we can visualize all the footprints of the burst that are intersecting our area of interest. So then the user can select the burst ID that best match the area of interest. The notebook can also show a calendar of acquisition, including all the tracks that are intersecting the area of interest with a different color for each acquisition geometry. And then, as I said before, plot the interferogram network with the temporal baseline and the perpendicular baseline for the automatic extraction of the interferometric pair list, which is the input that we are using then for the OpenEO processes for the generation of the time series of interferograms. Here is simply the definition of the OpenEO processes for this case. So as you can see, again, simply specifying the process ID, in this case Sentinel-1 SAR interferogram, and the input, the insert pair list, which can manually specified, but of course is much easier for most of the cases let generate this automatically, specifying some criteria on the temporal and the spatial baseline from the Python notebook that can be executed in CDSE. And then all the other parameter burst ID, sub-SWOT ID, and so on. So then we finally have our time series of interferograms, and we try to ingest it in MinPy. So with a little bit of reformatting, and the reformatting procedure is also available in our GitHub repository that I will show later on the conclusion. We could simply ingest in an easy way the interferogram time series in MinPy and operate our deformation analysis. This is the result of the deformation analysis done with MinPy, and then we also compared for a specific point, in this case, the result we obtain with using our inputs, so our interferograms, with what was achieved in the MinPy tutorial using the Alaska facility time series of interferograms, just to have a look if we have a good agreement or not. The agreement is good. There are still some small differences that are possibly caused by some small difference tuning parameter, for example, on the filtering or multi-look parameter, which were not so explicit in the MinPy tutorial, so in the dataset that was used in the documentation. So before concluding, a few words on the performances. So as you probably know, the CDSE works with a credit system. So every user, every registered user can have 10,000 free credits per month that can be used for doing all the processes in CDSE using OpenEO. And just to give you an idea, the generation of one interferogram of coherence on a single pair consume a couple of credits with a base cost for the initialization of the process of around 7 credits. So just to give you an example, the generation of how was it, 43 pairs for a specific case in the Andes consumed around 90 credits, so a little bit more than 2 credits, and 28 pairs, 64 credits. A word about the processing time. So a single pair processing takes around 10 minutes for a single pair, for a single burst with a 7 GB RAM allocated, which is generally done. However, concurrent jobs can be executed That means that jobs can be, you can produce pairs in a parallel, in a concurrent way. And just to give you an example on the use case I presented on the glacier, where we generated 190 pairs over 25 different bursts, we created 25 different jobs that were run concurrently, and the entire processing ended in around a couple of hours. Okay, so then to conclude, we have now new OpenIO capability for processing SLC data. And this can be done by all of you by simply registering on the Copernicus data space ecosystem. You have, every user have these free credits that allows to play a bit with this and generate quite a large amount of interferometric data without cost. The documentation of the processing is available in the Apex algorithm catalog. And if you want to know something more, please check our recently published web story in the EO4 Society web portal, and also check our open GitHub repository, in which you have all the examples of how to generate this product, and also more detail about the implementation.
Thank you. Time for one question. Quick one. Anyone? Here down, please.
Just quick technical question. Whether you used this facility together with MintPy, is it like that you have to download the data from the server, or you can run the MintPy also on this environment?
No, for the moment you have to download the data and then run externally. Yep.
Thank you, Mattia. So
now we can go to the next session from José Manuel Delgado Blasco about feed-down, which is
yeah, and SARPix. Yeah, thank you very much, Captain. So, well, I'm going to present the work that done by Roberto Del Prete, a colleague of mine from the Phil Lab that could not come today. So, as the title says, I'm going to talk about two Python packages that allows to get from CDSC as well to geocode the interferograms, bar-centric approach. So, yeah, just a few words. So, what is the ISA Phil Lab? So, we are a division within the OPS in the science department of EOP. And, well, the head of the division is Giuseppe Borghi, and we have there two different sections. One is more dedicated into science, research, and exploration, and the other section is more into the supporting companies in the commercialization of Earth observation-derived products. So there in the division, we can see activities going on quantum computing, foundation models, onboard data processing, etc. So as said, we have two different groups there, which funnel one to each other. And this presentation of today actually is coming from the Explorer office, in which they are doing a lot of data processing, as many of them are also data scientists, doing sort of things with AI. And they needed to process a lot of data sets from different missions to get access to them and to do their own magic to do machine learning ready data to their own applications and research. So basically, they start developing the feed down, which actually is a Python interface that allows you to download any dataset from the Copernicus data space ecosystem, and also to match different satellite missions acquisition timing, Sentinel-2, Sentinel-1, also FISA datasets, and many other more. So I will invite you maybe to explore them later. And then they start developing also the SARPix, which actually is a Python wrapper of Snap as well. So they needed to have operational routines that are able to process data systematically in the same manner. So they start to work with this approach of having a Python wrapper that is able to invoke GPT, from a snap and with some defined recipes. So yeah, basically, as I said, they did all these couple of packages, and they are both being able to execute purely in Jupyter Notebook, which actually makes use of pip, sorry, for installing the SARPix and also a feed-down, but also created a conda environment of Snap itself. So you don't need to go and download the Snap. For example, in this version is the 13 one. You can just conda install, and you have all the dependencies on it. And yeah, well, that allows you to be more portable and install it anywhere on any environment and run it locally, differently from the previous solution that was cloud-based. So here, I just stole the burst picture from the presentation from the EO4 Society website. So indeed, I mean, before we are used to download entire SLCs, which now from CDSC are like 8 gigabyte each, so it makes a bit data download a bit heavy. So yeah, having now the possibility to download single burst in the case that your area of interest actually suitable for this small data processing, it's quite convenient. So this feed down allows you also to invoke the on-demand request of the burst level download to get everything locally and do your own processing in your own laptop. So as I was mentioning, it has been defined recipes for which, based on Snap, is able to do also, in this case, interference, which was one of the applications, a part of calibration and terrain correction that usually the machine learning processes also use. In this case, they also needed to do interferometry and coherence. So they use as a standard workflow from Snap, and it was totally being able to be called by Jupyter Notebook, as I said, and just execute it locally. Obviously, this you can then install it into Google Colab or any other on-cloud notebook, Jupyter Notebook based. And yeah, you have the data, and you download it, and you interpret it, basically. So as I said, the first thing was just to mix all these satellite missions to be able to download it using feed-down. So for this, it was quite, I think Roberto announced it in LinkedIn a couple of weeks ago, and it was quite a lot of impressions and likes and all the stuff. So then, obviously, the workflow for interferometry, it helps you to search actually the more suitable pair in terms of perpendicular baseline and temporal baseline separation. And yeah, basically you select the area of interest, and it's able to auto-select whether the best suitable data is ascending, descending, or which orbits to give you the higher spatial coverage. Yeah, so this, with some parameters, you can define whether the polarization, what you want, and so on. And yeah, as I was mentioning before, all this is obviously burst-based, so the recipes that they are integrated there but can be expanded are for now only based on the burst SLCs interferometry, so they don't have top-side split, for example. They also don't have the bursting operations. And yeah, just putting your account credentials, you are able to download directly into this Jupyter Notebook or any other local environment. What else? So yeah, you basically just need to define few parameters as you wish. So you want DM or pixel spacings, because this is actually at the end ends with the terrain correction products for machine learning algorithms that they were doing. And just defining a couple of them, you are able to automatize all the process, as you are many of you very used to do. So yeah, you may see the different steps there, or you may let the machine to do all the different processes for you. You get two outputs, the interferometer and the coherence from all this chain. Then you may get also the plots and everything. I mean, in the GitHub, I will put there later the QR code. You can get also the notebooks which do all the recipe for you. So you may remember as well that some years ago, I also did some Python snap to stamps to allow the time series interferometry. So I talked to Roberto and say, oh, what you have developed is really cool. Actually, the snap to stamps is not still updated to do single burst interferometry, so maybe we may bring it into the SARPix. And then is what we did. So now with this SARPix, you find also a recipe that does exactly the snap to stamps. So it does not do the final terrain correction, but does the stamps export basically at the end. All the different processes are the same. Yeah, and then you may get the full time series interprograms, and then you can then use the stamps by your own workflow you may have, and so on. But just basically last week, well, this is the team that had been maintaining the different tools. And basically last week, Roberto told me, well, but I completed the renewal of stamps into Rust. So now you can, again, well, the name is quite unfortunate, so it needs to be renamed probably. I already mentioned this to Roberto, this existing official PyStamps from Andy Hooper. I think this was announced this morning. And but you can also download it from the GitHub repository. It's still under testing in the sense that it has been newly developed, entirely the full chain, but the testing in many areas of interest needs to be still checked. So this has been developed basically using only a couple of areas, a couple of data sets for which the final performance in terms of PS, accuracy, coherence are exactly the same, matching with the stamps, but the performance and time and resources is quite improved. So as I said, this has been entirely ported into Rust. So now we are in the testing phase, but for the first test we did, basically we saw exact match in the time series within the standard stamps chain. So there was the version 4.1, I think there was the last one until this morning. And yeah, so there was perfectly matched in the time series. So in case you are interested to run it, I will put the QR code later in the slides so you can download it and play with it and come with any feedback if you find anything to be fixed or verified. So now with this, basically you may have everything you need to go from the CDSE single burst up to the time series processing with the stamps using this new Rust accelerator of it. So in case you're interested, you may do some pictures on the screen now. I think it's quite interesting. I mean, you may go to the Philip GitHub and then you find them there, but you may play with all of them. As I said, the PyStamps is still recently released, so it needs to be still some verification to get everything just set up. It still has the same dependencies, so snafu needs to be installed, triangle needs to be installed, but all the MATLAB code is not MATLAB anymore. So yeah, so the next one I think includes the QR for the entire fill-up GitHub repository, and that ends my presentation. So you have any questions, I will be happy to answer.
We have time for question front here.
Thanks, Jose. It really looks amazing. Two technical questions again. First one, what about ETAT corrections? And the second one, is it still only on burst only? I cannot stitch more burst.
No stitch them, but I mean, we could expand the recipe to work with the entire stamp-to-stamps was working with the entire SLC. The ETAT is not yet integrated, but it could. I mean, Snap, I think, has already the operator to external plugin, I think, to read the ETAT correction. So it could be integrated actually now easily because it's also all Pythonized. So it could be done in it. Thanks for the remarks. Any other question? Okay.
Julie, I have one.
You have one. All right.
You said that the full chain automatically selects the best pairs. How do you define a best pair in terms of interference?
Yeah, I mean, I was saying that it takes into account your area of interest first to verify whether it is ascending, descending, or which is the track is actually taking the more spatial coverage over your area of interest. And then it takes, I think, the shorter perpendicular baseline and temporal baseline. And you can read the perpendicular baseline from the metadata and out of these in S3 packets from CDSE. Yeah.
Thank you.
Yeah, welcome.
We can move to the next section, to the next presentation. which is from our colleagues from FlatSim for the processing of Sentinel-1 data. So the floor is yours.
Good afternoon, everyone. So my name is Brian Rimbaud. In English, you can also say Rainbow, which makes it funny given the name of the workshop, like Fringes. And today I'm going to present on the behalf of a lot of people that has worked on this operational service in France that is called FlatSim. This is a service dedicated for large-scale ground motion monitoring with Sentinel-1 data. So FlatSim stands for Formater Large-Scale Multi-Temporal Sentinel-1 Interferometry. Formater is a national data hub in France that supports Solid Earth's project and provides some infrastructures to do them. So it's a project that started a long time ago, like more than 10 years ago, right before Sentinel-1 was launched. With internal discussion at CNES, the French space agency, of how can we manage this large amount of data and process it for the scientific community, especially in France. So the initial objectives of this project was to process Sentinel-1 data on the CNES HPC for large area over 250,000 square kilometers beyond the capabilities of most researchers alone. It's a service that provides time series using the NSBAS multi-temporal chain. It's a distributed scatterer chain and also provides some other products. And it's an automatic workflow that works with minimal parameterization and that is validated at the end by INSA experts. The main objective at first was to support scientific usage in France, and then it has to be opened widely after a restriction usage period. And this is also why I'm presenting here today. The first call of IDs will be released, and so that a large amount of data that has been processed through this service will be available to everyone. And one of the objectives as well is to enable incremental processing for future calls, because, you know, way to go Sentinel-1C and 1D with 10 more years of data. So far, there's been like 3 call of IDs with 27 projects selected, and I'm going to present most of them. So the processed areas so far are presented on this map. You can see in red the first call of IDs that covers some areas around the world between 2014 and 2021, and you have also the result of the second call from 2014 to 2022. And after those 2 calls, we have generated more than 170,000 products for more than 600 terabytes of data and more than 12 million square kilometers of geographic area. And the most important thing to know about this project, it is for and from the geoscience community, right? So you have here a lot of projects. Oh, this is a laser, gotcha. So you have all the names of the project there, and they have like thematic applications like such as landslide, tectonics, volcanology, and they have been chosen by project leaders, and for most of them, they are INSA scientists in France using those data. There is a third call of proposal that is ongoing. Actually, it just terminated a few weeks ago that will process data from 2014 up to 2025. And you have it there on the map. And this will result in more than 1 petabyte of products, mainly incremental, because some of the areas that are presented there actually overlap the one I just showed before, and resulting in more than 15 million square kilometers of unique geographic area processed. I will dive a little bit into the algorithm. This service uses FlatSim, this service uses NSBAS algorithm that is actually a multi-temporal INSA processing chain using distributed scatterer that inherits from ROIPAC, from Rosen and collaborators, and with state-of-the-art developments over the years. And one of the thing with this processing chain, it enables processing scale that are very large over the azimuthal distance, which actually enable long wavelength deformation signal extraction independent from GNSS. We, as some of you may know, we also have sometimes some trouble to select the burst, so that we actually loop over all the safe archives to actually detect the bursts that covers the area that we are looking at, so that if the frame is inhomogeneous, we actually check all the save files so that we have all the bursts and maximize the spatial coverage and temporal consistencies for large area processing. Well, the chain, I would say, is pretty classic, right? I mean, we are not revolutionizing the INSAR processing, but we do use some tricks to make it a bit more interesting, right? So, for example, we do correct from atmospheric data before any unwrapping, so that we can basically facilitate the subsequent unwrapping by reducing the phase discontinuities. We also implemented some tricks in the unwrapping algorithm, so that we implement a region growing unwrapping algorithm that starts from high quality pixels, so that those ones we are pretty happy about it, but the other ones will be a bit difficult to unwrap, and we prioritize them compared to the other one to minimize any potential error propagation. And we also automatically bypass that areas that are affected by layer over to ensure accurate unwrapping. And you have here an example of this framework, and right, so for example, there you have the wrapped atmospheric phase screen that we use to correct before any unwrapping, and that is just there. We also use network inversion strategy, such as using long temporal baselines to limit phase bias and integrate noise better, as it has been mentioned also in the other room, and following the recent papers. And for example, there we select the 3 closest pairs, the dates, to the one of interest, and then one at 60 days and another one at 1 year, so that we have temporal baselines that actually mitigate, do not fully correct, but mitigate any phase bias that can happen in the interferograms. We also do pixel per pixel inversions, well, pretty classic, that enables mapping of residual for each link, so that between each link for a given pixel, we can have the residuals that is used as a weight for a second iteration. And in this second iteration, we add the weight and also a value that is a factor of 2 pi radians that is applied for iteration on the incriminated residuals links to reduce any potential phase bias or unwrapping error. Well, we are giving a lot of products, and it will be available in the future, but we all start with the wrapped differential interferograms at the 2-look resolution. So what you have to notice there is that every time I'm going to go on another category, you multiply by n the number of data that we add to the archive. We also provide filtered wrapped interferograms and also the unwrapped one, so that if you want at any point to go back to the original data, you can. And also provide some atmospheric phase screen derived from Error 5 and spatial coherence maps for quality assessment. And all those products are actually described on the website you have here, and so that you can go in detail and have more information about it. We also provide 8-look interferograms for a resolution of 120 meters, and also 16-look interferograms. There are some quality indicators also in this data set, such as the RMS misclosure, the temporal coherence proxy, the number of images, interferogram use, and of course, the time series package that is actually displacement data cubes with cumulative phase delay in radians at each time step. We also provide some mean line of sight velocity, and yes, I didn't mention it, but it's in ascending and descending, of course, orbits. And we also have auxiliary data package, so that it might not be ARD proof, but all the information that actually are in the IRD format actually present in this data set. So, well, we might have a little bit of work to do on that, but it will come at some point. And we also provide the lookup table, the temporal coherence, well, anything that actually might help you in your analysis. And it has been asked to us to find the French researchers so that they can do whatever they want with the data. And most products are actually available in both radar and geographic coordinates, so ×2 for each product, with previous PNGs and metadata. And all of that is in GOT format. Well, that's it for the data set. Now, let's have a look a bit of at the results. This is a paper that is in preparation by a PhD student in France that actually used a data set over Turkey, and they almost did no post-processing, meaning that they might have referenced the frame one to another, but you can see quite clearly that it's pretty clean. We do see some delineation, but on most of the tracks, we do not see them. Well, remember I told you it's between 2014 and 2021, so we don't see the Kahramanmaraş earthquake, but we do see the Elazig earthquake that happened in 2019, I remember. I'm not sure. Some people probably in your room knows better. Another example of this data set is that, in some areas, it might be difficult to use interferograms because well, the clearance or is not as good, and you basically cannot unwrap correctly, and you have some trouble. For example, here in this region in Botswana with the Okavango Delta, they used another product with actually the coherence time series to identify the flood pulse arrival. And you have here the color bar, which is actually a very interesting way of presenting this color bar. It's the first time I see that. It's basically you have like a block, and depending on the days of eye exchange, you have the color, and depending on the average, you have like a average coherence, there's more or less opacity, and then the ENSI actually makes it black or not. So basically what you can see there on this small area is that you have the flood pulse arrival that is actually well delineated. And it does match with reference inundation maps that also detected this area with other data sets. Well, so I'm here today to present you that we're gonna let this dataset open. So what it is the Sentinel-1 SAR interferometric products covered in 2014 to 2021 over 7 regions: Ozark, Central and Indies, Balkans, Turkey, Tarim, Afar, and Okavango, spanning 5 million square kilometers and more than 300 terabytes of products. For who? It's a research and non-commercial entities only under the CC by NC license. And when it will be in, at the end of this year in the Q4. Applications and what for? Actually, I mean, now it's up to you. I mean, the data will be open. You can do whatever you want with it. And one example might be a study that has been done recently by Burroughs and collaborator using the data over the Central Andes and using the wrapped interferogram to basically label the landslides occurrences in the wrapped interferogram so that you can train a machine learning algorithm that can detect any precursory movement on the landslides, and so that in the end there might be some interest like to do some kind of landslide observatory over a country, for example. So, and how can you access the data then? Well, there is a DOI, and everything is explained on that website that is linked to this DOI, and there's tons of information. I cannot read them all, but to you right now, but yeah, please go and see for yourself. Well, the web page will look like that. Basically, you have all the areas that have been covered, and you have to click on either the project you want, and then you will have like a list of the products such as interferogram, the wrapped one, the unwrapped one, the coherence, and get the packages that you want and need. I would like to highlight now the benefits of this in France with some usages and statistics, because it's a work that supported a lot of postdocs, PhD students, and interns across France, with a lot of permanent researchers, I mean, for the size of France, of course, and with more than 10 scientific papers released since the initial data release in 2021. There's been a bit of a latency due to the publication pipeline, as you all know. And the results from the first call are now arriving, and it's a ton of data and new science stuff that is pretty neat. And so, yeah, look at them. It also led to the development of tools because a new massive amount of data also implies to develop tools to look at them. And for example, there's been a InService, which is a data cube visualization tool that is very interesting to look at the data set, plot time series, and also some profiles. And in France, it also triggered the organization of dedicated national events such as the FlatSim Day and conferences. And yeah, I would say that now and more today, we have like a dynamic scientific discussion around inside in France, and definitely many more to come. Well, I always wanted to do that, you know. I've always seen people highlighting the work of others and saying, oh, look, they are using our data. It's pretty neat. And don't miss our talented PhDs and postdocs. They have been doing a great job using the data and doing great presentations. So some of them are Thursday, Wednesday, and it's pretty neat what they're doing. And we welcome all your questions. And especially the posters, go and see them. It's really nice. And lastly, I would like to thank you for your attention first, but also thank all the people that have been involved in this project that has made this journey possible by the efforts of so many people, as I say here, across France. And so I stand here on behalf of all of them, but so thank you to all of them. But those 3 small dots is probably because I'm missing a lot of them. But thank you for your attention, and I welcome any questions.
Are there any questions? Please.
I have the question whether the data from this beautiful project will be available, like, for example, the layer of displacement that I can load from my GIS, for example, and use it for further analysis.
Actually, this is what I say. You will be able to use the data as you want and look at the data cube of time series and do any comparison that you want with other data sets, for sure.
Philippe Belli from ISA. Thank you very much. I have a question. You have a very interesting way of representing the Okavango flooding features using the hue, saturation, and so on.
Mm-hmm.
But my understanding is that coherence for flood monitoring doesn't work with 6-day coherence images. You need 1-day coherence, and IRS tandem was 20 years ago. How do you do that?
For sure. I mean, you still have coherence with 6 days interferograms, and you can still show things as I showed to you. But yeah, for sure, it would be better to have a 1-day interferogram to do, well, a very precise coherence delineation and flood time arrival. So I recommend you to go on that paper and look for yourself. And there's probably some uncertainty about the precise date of arrival, either other data sets to that actually constrain it. But yeah, I mean, it's up to ESA now, I mean, to provide the 1-day interferogram and the possibility to do that, or any space agency.
Any question? No more questions? Thank you very much. So we give now. Okay. I'm going to call Mark Penelans to present anomaly detection in insert time series. Thank you.
All right, so my talk today is going to be maybe a little bit different than the other talks we have in this session, because here we really want to take it a step further. So a lot of the sessions in a lot of the talks in the session go about, well, here's some products that you can go and inspect, you can play around with, but how do you actually go about making decisions from these data? Because that's what a lot of this ends up being used for decision makers. Those decision makers don't really know the ins and outs of insert processing, and definitely not exactly the history of processing behind all of these different products. And so here I want to present some of the tools that we use at SkyGeo to help these decision makers. And to do that, I want to first show you what often is kind of a default product, and that's a static velocity or total displacement map. So this can show you areas that have moved in the past, right? But it is non-interactable. It is not dynamic, right? So you can't actually show the time series from here, or if you do, you tend to focus on the areas that have displayed the most, or that maybe look interesting from just this map. And if we're talking from a monitoring perspective, these types of maps, they don't change too often unless something pretty major has happened. And now I want to go to the decision makers. They often come with questions like, well, I want to know when something changes, or I want to know precisely where to look first. And these questions are sometimes hard to answer with these types of products. And so you need to basically help them along, do consultancy to bridge that gap between the data and their knowledge. And to do that, one of the tools that I should take one step back and talk about one of the requirements that these tools that we use should really have. Well, for start, they need to be simple. They need to be simple enough to be explained to these non-INSAR experts. And that way, they can go and use this data in their decision-making. They need to defend the decisions that they're making as well. It also needs to be general. It needs to fit a wide range of applications, right? So it cannot only be used for very wide area products. We've seen already this week talks about nation or going into continent scale processes, right? This should also work at a local scale. Then, very importantly, it needs to be tunable, adaptable, because one man's noise is another man's signal. And I'll go back one slide to show you this time series, right? Some may see, okay, this is just a downward trend. There's no variation about it. Others may say, oh, there's actually plenty of variation, and that's what makes it interesting. So it needs to be able to pick up that variation, whether or not it is interesting for these decision makers. And lastly, it needs to be scalable. You need to be able to use this on a large data set. And that's because at the rates that we have been producing data, and we had the previous talk before with 650 terabytes of data being produced, products being produced, right? We're outpacing our ability to inspect all of this data that we're generating. So I want to talk to you now about one of these tools that we use that's based on the QSUM algorithm. And the way that this works is that it takes the displacement time series that have some uncertainty, there's some residual noise in there from these displacement time series estimations. And on the other side, we have a model that tries to explain this displacement. This model is really where you can put all your knowledge into it. And you can make this as simple and as complex as you want it to be. But in the end, you'll get some residuals. And these will tell you if something is moving as expected or if it's deviating from that. And it's these deviations that are then important to us. And by processing these carefully, because we don't want to trigger on just a very minor deviation that falls back immediately to the expected signal, we can get to these QSUM time series that show when signal has significantly deviated from the expectations. Now here is a simulated example. So I've just taken some generated a noisy time series that will deviate from the expected model at about day 1020. Will deviate slightly, and what you'll see is those residuals, they change, and this QSUM at the bottom, right? So let's see. Oh, that's not what I wanted to do. There's the pointer. Right, so these residuals here at in the middle, they still hover around, right? And then this QSUM time series reduces those residuals to something much less significant in magnitude. So it's easier sometimes to inspect these. And then you see, I'll wait it one more time, you'll see that strong deviation happening from about day 1020. The detection happens slightly later because these residuals, they need to be accumulated to some significant level. Now, this is just a simulated example, and I want to now go through several examples, real-life examples of different applications. The first one is localized subsidence on a heap leach. So heap leach is a structure used for mining to extract ore, and they tend to spray these heap leaches with acids to leach out material, often gold ore. And slope failure of these structures can be very deadly and very polluting to the environment. And so here is an example where the model that I've used is a lagging linear fit to the time series. You'll see this big deviation. Now, this is really maybe a bit on the big side that you would already see otherwise, but it highlights this, this method quite well. Was that at some point it really deflects downward. There's this change of expectations, and then it slowly recovers from that into kind of a new normal. And that's why here I chose for that lagging linear fit. Then I have a second test case, which is a tunnel in the Netherlands. And this is quite a special case, because here they actually noticed that a segment of the road going into the tunnel started to uplift so significantly that they had to weigh it down. Otherwise, all the cars that would drive over would start basically bouncing, destroying the road, destroying their suspension. And they had to put literal tons and tons of sand on there for a really long time. I don't know exactly from the top of my head, but this tunnel was out of commission for, I think, over a year. And when we look here, the base model here is quite simple. There should not be displacement of these along this road. And so what you see here, let's first focus here in the top right, you'll see the displacement, the total displacement that occurred over the last 5 acquisitions. Now this jumps around quite a bit, and if you inspect it quite carefully, you'll see a bit of a seasonal signal in there that varies from the northeast to the southwest side of the, the northwest to the southeast side of the bridge. But we're focusing here on one section that rose the most. And you'll see that there are some variations, but here we're really talking at the millimeter level. And it's a decently long time series, but I can use this to explain another aspect. So to use this tool, you do need to allow for a bit of a buffer period to set your expected model. Residuals very early on in this time series can throw it off. So you see this green dotted line. That's what we call a burn-in period. So the period before it is used to help build up and let's say build up and confine the solution here. And you'll see that this section that's highlighted, it deviates from the rest and it stays deviated. So you'll see some others that are highlighted here that will get highlighted here pretty soon. Those just make maybe 1 or 2 blips. Those could be outliers in your estimation. Right, so one time it shoots out and the other acquisition it goes back, so there's a couple there. But when you have this continuous offset, right, like the segment here, that's where you know there's an anomaly that's taken place there. That's what I should inspect. That's where I need to look first. And now let's go to the third and final test case I have from this. And that's oil fields in Southern California. Now, this is quite a heavily exploited area, and they are very careful with their subsurface pressure management. So they inject water as well to keep the pressure in the subsurface high or to actually push out the oil. And something that can happen is when a well, for example, gets compromised by some seismic activity of the faults there, you can get these things called blisters, or very localized uplift signals. And so both this long-term pressure management we want to track, as well as these rapidly developing blisters. So first, I'll show a section where we try to track this pressure management. So here at the top, again, we'll see the total displacement over the last 5 acquisitions. Here again, I'm using this lagging linear fit. You'll see the residuals, and then you'll see skew some analysis. Now, just based off of this, it will be very hard to tell exactly where to look. But if I go down here, here it starts. You see this big negative deviation followed by a slight positive in here. That's where we see this change in their subsurface pressure. And this ties up very nicely with the context here of this area where they actually had to change their pressure management due to regulations, and we could track this very well. Now, here is another example where I highlight one of these blisters. Now, if you looked very carefully, you may have just seen one already. That's responsible for these early jumps in the residuals. But another one is going to happen right here, and we see it tracked that one as well, quite well. And interestingly enough, this area is less affected by that pressure signal that runs through now. It's actually less affected by that signal than the surrounding area. So using these tools can actually help us identify some very minute details of the displacement signal and possibly the interpretation of those. Like, what does this mean? And that may be very important to those decision makers. Now, if you're still not convinced that this works, here I also have a static example where I fixed the model between the starting and the end date. And here I show both the temporal progression. So that's right here of one of these sections. So these sections are all of the wells you saw in that previous image I showed, as well as the change in this Q-sum value for different time segments. So you can see that it really starts, localized area, it spreads out, and it actually partially recovers as well. And so this is just one of the tools that we can use to try and answer all of those questions, right? We just want to know when something changes, or does this happen because of something that I did, right? And that's exactly where we, I think, can bring this additional value. We're all experts here, but we need to make that translation. And for that, we need to have tools like this. And I just want to go back to some of those requirements and a basic summary of my talk, and that's that these maps of linear and total displacement, they will hide a lot of important information. And that interpreting this type of data, especially at scale, requires us to have tools that can identify these anomalies for us to look into. So there's simply too much data to investigate on our own. And we cannot have just one tool to be used everywhere without it being adaptable. We need to be able to fit this to the specific applications. And then lastly, we shouldn't make this overly complicated, because then it cannot be defensible by people that maybe don't have all of the knowledge that went into the processing of these data. And with that, I want to end my presentation. Thank you all very much.
We have time for questions. On the upper right.
I realize you said don't overcomplicate, but have you thought about making it more complicated by accounting for the spatial structure of anomalies you expect? As in, is there, like, the CU sum is pixel-wise, correct?
Yeah, so in these examples, I have aggregated results as partly to increase the signal-to-noise level, but this tool can work on the individual scatterer level as well. So and that really is going to depend on your application. If you're going to process, let's say, data over an entire country, you're maybe not going into every scatterer individually. But if you are looking, let's say, at a bridge or at a house, maybe you do want to go to this individual scatterer level. And yeah, this tool is flexible enough to allow that.
Like,
just here in front of me on top.
Hi, Mark. Just a quick question about to what degree does noise affect that burn-in period? And what if in that burn-in time you have other real jumps in the time series?
Yeah, so this is a very valid question. So this method works by incorporating the spread of residuals in the past to identify whether change in the present is significant. And so, yeah, major deviations from your model in the past, in that modeling period, they can really impact this. So if you have that, then you need to either include that into your model or specifically say, I'm going to only start again from my kind of new normal. So this, you need to be a bit adaptable in that sense as well. And it can be, yeah, basically sequential anomalies that you want to investigate as well. And so by separating per anomaly, basically, you can, you can inspect those individually. So.
Can I? The question is, Hi. The question is, what you showed us are operational products that you give to clients or are simulation based on real case? Because the question is, if those are operational services, what do you give to your clients? You did an announcement that the threshold passed, and then is there some kind of framework? Because if we are speaking of mining area, of course, you are alerting them or something changing, I guess they will need then to put in place some actions.
Yeah, so I would say that this is not just an operational service on its own, but it's part of the consultancy that we do at Skagier. So it's one of the tools that we use to actually help the decision makers. So on our side, we have the knowledge of the in-store processing, and they may have very relevant context to interpret these types of results with. And this is just one of the tools that we use to help with that interpretation.
We have one question on the right side here. There is a mic available.
Thanks. You mentioned at the start that there's a delay happening in between the detection of something because you work with like a sliding window. I was wondering what is the magnitude of the delay and how like scalable is your approach to work with, respond to different types of changes that happen, that you expect to happen over longer scales or over smaller scales?
Yeah, so there is going to be a little bit of a delay, and that depends on how significant of perturbation basically there is to from your expectations. If it is very significant, you're likely going to see that already in other more rudimentary problems, like just a 6-day, 12-day interferogram. So this tool here is more so to detect small, minute changes that can accumulate over time, or small, minute changes that maybe has happened at a very specific moment and then have basically fallen down to a new normal. So like a step change, for example, this method would be very well at detecting. And if you want to, you can actually have it alert earlier. The counter to that is you may alert more frequently when it is actually not a deviation. So the counter to that is you may have more false positives. That's it.
And we had the last question over there.
Yes, I have a question about the data set. Does your algorithm work also in shorter data sets? How many images do you need more or less to define a model?
Yeah, so this is also a very important question, right? So there's very much a reason why I have set this burn-in period. So you need, first of all, you may need a few dozen acquisitions to build a confident time series. That's one. But then second to that, you should maybe not interpret these results on the very first acquisitions, the very first changes in this time series, because you need to build up that distribution of residuals. And so this is basically the example with the shortest pre-period. And you can see that partly it works here because the residuals around this, around our model here at the start are very low. If the residuals were fluctuating more, right? So like, for example, in this example, then you would see more variations at the start. You maybe get more false positives that way.
Thank you very much.
Thank you.
We can move to the next presentation, which will be given by myself. And so, good afternoon, everyone. Thank you for coming to this session about processing environment and operational services. Today, I wanted to talk a bit about Hamster, which is an open source toolbox for automatic multi-sensor in-service processing and multidimensional deformation time series. I'm Quentin Glaude. I'm working for European Center for Geodynamics and Seismology. And so if you want to know about the life of a Hamster user, basically you arrive at work, you discover new results computed during the night with deformation maps, updated time series, quality control reports, and also geocoded results that are all hosted on a dedicated website where you can basically everything which was scheduled and performed as soon as one image is available. So the first question you may ask is why and what is Hamster? What is Hamster? It's a collection of three components. First, Hamster engine, which is a C language binaries that do basically all the interferometric processing, which includes the data reading, the co-registration, the interferogram formation, the filtering, the unwrapping, the geocoding, and so on. Then you have MS-BAS, which is a model for inversion, so that you can take the unwrapped interferograms and produce a 3D or 2D time series. And then you have a null orchestration tool, which is composed of bash files that basically wrap the MS-BAS and the Hamster module together to make it something operational. It is based on a few decades of developments. It handles quite a large amount of different satellites, and it's fully open source, so you can download and process it yourself. If you look at the INSAR processing ecosystem, which is not exhaustive, but just some examples, you have nice commercial suites such as Gamma, you have excellent educational tools such as Snap, you have also processing capabilities from FlatSim dedicated to Sentinel-1, and in that ecosystem, Hamster is just complementary to these tools by providing an independent implementation of all the things that already some other people are doing. But I think it's important not to everybody use exactly the same tools, but instead let the result be cross-checked, because that's how we make debate in science. And so Hamster is participating in these discussions in science. Who is using Hamster? So Hamster is used by the European Center for Geodynamics and Seismology, which is the main developer of the core toolbox. Then you have the Liège Space Center, which is doing the co-development of the Hamster engine. Then you have different partners in France, in Africa, and Canada. And now we are working also with GEPS, the GeoHazard exploitation platform, for later integration that I will talk about, but also many researchers worldwide. So one of the strengths of Hamster is the large number of satellites from ERS to NISAR and soon biomass. It can handle basically everything, and all these data reserves are built in-house, meaning that we don't rely on someone to do it before us, because we basically do it ourselves. So meaning also that if you want to process commercial satellites or satellites that are not usually processed by other software, if we have the specs and test data, we can also provide a data reader. The last one to join the family is a NISAR, which is ready for quite a long time, but it was tested first on February 2026, when we received a batch from the Alaska Satellite Facility over central Nepal, where we have a 3-month time series, which help us making sure that our full chain is working properly. We have a preprint on ESS Open Archive, so if you want to know more about that, don't hesitate to download and read the article. If you want to go into more details about what's inside Hamster Toolbox. So Hamster Toolbox is a command line toolbox, no graphical user interface. Every step is a shell command, and all these shell commands are composing the Hamster Toolbox. It includes reading all the image, preparing a mass process co-registration, but also preparing the MS bus and all the different pairs, the network from the baseline plot, from the MS bus inversion, but also computing the time series and so on. And all of these scripts are calling Hamster engine binaries written in C that are computing the data reading of the images, but also performing the co-registration and so on. When you are using Hamster, you probably want to use first single pair bash command, which allows you to have a full chain on one pair of image, from the data reading to the geocoding. And from that, you can fine-tune the parameter before scaling up to a mass processing. So once you have set everything, you can basically process hundreds of thousands of SAR images with this classical full chain, which comes from reading all the images, making all the co-registration, preparing the MS bus, doing the interferometric processing, the filtering, the unwrapping, and then doing the inversion to get the three-dimensional time series. Of course, all these bash scripts have helper functions so that you can basically understand how to use them. And that's it. And it's not just a black box toolbox in the sense that you can basically parameterize at every step. You have a lot of opportunity to change and tweak depending on your study case. For example, for the preparation of MS bus, if you are worried about the computation times from the interferometric pairs, you can decide to have not too much dense networks so that you can optimize the number of interferometric pairs in order to get less computationally intensive. If you have, if you need different perpendicular baseline, for example, because of the failure of Sentinel-1B, the orbital tube is getting larger, you can also define different perpendicular baseline in case of this event. Maybe you don't want to have too large temporal baselines, so that's something you can also set up. And so at every step, you can basically fine-tune everything you want. And that's make it not a turnkey project, but more like a research-grade toolbox for people that know about INSAR. And we are making also these tools for the people to reach these goals. And of course, the end goal is to combine every geometry to produce three-dimensional displacement time series. So as input, you have the unwrapped geocoded interferograms, and in the end, you get the 2D displacement or the 3D displacement if you have a large diversity of geometries, or with some kind of assumption. So then, in terms of operational services and processing environments, which is the name of the session, at ECGS, we are working using cron jobs. So if you are familiar with the Linux ecosystem, cron jobs are scheduled tasks that you basically create in advance so that you make sure that some tasks are running at specific times. In our case, for example, in the Central Nepal, we have 3 scheduled tasks that are running sequentially, from reading and co-registrating all the SAR pairs, then a second job for all the interferometric processing, and the last job for the MS bus inversion. Of course, behind all these jobs, we have also a lot of metrics, making sure that the things are going correctly, but also generate some quality reports in case you want to understand if something goes wrong, you understand why, and so you can reprocess the data in case of failure. We have also a dedicated web page for the observation of the results. It's not a fancy web page, but it's quite useful when you are working with partners, when you want to see the last deformation maps. You can also click on the deformation maps. You can click on different places on the map so that you can compute time series. You can provide your email, and then it gives you by email the time series once it's computed. It's yes, it's quite useful. If you don't have your own servers, but you have access to a HPC. Hamster engine is written in C. Is parallelized with OpenMP. If your favorite HPC has some easy build toolchain included, you can basically load every module you need, and then you can basically run the makefile so that you have your own version of Hamster available in your HPC. And if you are more into cloud processing, you probably know about the GeoHazard exploitation platform. So with a web-based interface, you can select a region, you can process the data, you can share with your partners. And the good news is that Hamster is joining as your GeoHazard exploitation platform, meaning that you will be able to process on JEP NISAR data, biomass data, but also ETAT data, and all the things that I explained before. So don't hesitate to stay tuned with that. If you want to know more about the Hamster integration into JEP, there is a web story about that on the JEP portal, so don't hesitate to take a look. And so does Hamster produce good science? So we have some studies around the world that include volcanic studies, but also slow-moving landslide, and other operational services. All this result was basically used for high-impact studies in nature, for example, with the Nyiragongo, but also in Kivu, in DRC, and so on. For example, I will take just 2 examples. In Nyiragongo, Hamster was used to produce the processing of the Sentinel-1, the ALAS-2, and the Cosmos Climate images to retrieve deformation near the Kivu region. And in Argentina, there were 2 slowly inflating volcanoes. And here, the Hamster contribution was again to produce deformation time series where we have near Laguna del Mol deformation up to 27 centimeters per year, which is already quite a lot. So these are still monitoring website. It's still something we can see over the website that I showed before. So that's quite useful for this type of study. Of course, whenever possible, we make sure that the results are meaningful. For that, for example, in La Réunion Island, we compare the INSAR time series with GNSS networks. So in La Réunion Island, there is a Piton de la Fournaise, which is one of the most active volcanoes on Earth. There are many GNSS stations available. And we see that we have a nice correlation between the GNSS and the INSAR time series. We can also look at that spatially. So basically on the base map, you have the deformation in the east-west direction and the up-down direction. And when on each dot, you have a color depending on the velocity average of the last 10 years. And if it blinds, it means that there is a correspondence between the two. There is a little white dot in the middle of the craters. That's because this GNSS is only 6 months old. It's not moving so much, so it doesn't represent the 10 years velocity average. But yes, it's still in preparation. In terms of resources, you have access to Hamster from the GitHub that you have at the bottom of the slide since the beginning of the presentation. So don't hesitate to take a look. You have already a lot of references of example, but also the installer, which is a very long bash file so that you can install little by little all the dependencies on your computer or your servers. You have also a comprehensive user manual, which is a very long PDF explaining about every possibility from Hamster. And we are working right now on some MKDocs material API references so that you can use you have a definition of all the different scripts with the purpose, the usage, the input, the output, the dependency, and so on, from all the scripts from Hamster. We always welcome new users. So if you struggle to install by yourself, you can always contact us by direct contact. So don't hesitate. We also offer on-site training. So if you want to go to use the European Center for Geodynamics and Seismology don't hesitate to send us an email. We can arrange that. It's fully open source, so just try it. We also organize some summer school and training session. For example, on the photo, this was at the Chambre de Commerce in Luxembourg. And the next one will be given in Nancy from the MD's 2026 Scientific Symposium. There will be 2 days dedicated to hamster. Just a slight advertisement. At Fringe, we have, if you want to know more about the recent development in the hamster engine, don't hesitate to come today at the poster session. It's poster number 1, so you cannot miss it, about ETAD management in hamster, but also the current tracking in hamster, and you will have the chance to meet Dominique Dereau, which is the lead developer of hamster engine. We have also a very nice talk as a case study enabled by hamster tomorrow at the Volcano station. It's in Piton de la Fournaise in the La Réunion Island, where Delphine Smitarello will present some result of by producing 1,600 ALOS2 images in 22 acquisition geometries. So that's quite a very nice data set. Yeah, so to conclude, Hamster is an open source automatic multi-sensor INSA toolchain. It goes from the download of the image to the web dissemination, so it basically do everything. Everything is built in-house, from the data reading to the registration. We don't depend on other tool chains, so that's also a lot of work, but it makes us also independent in terms of implementation, which is quite nice in science. If you have questions, I can try to answer that.
Thank you. Thank you for the presentation. Any question? Here down, please.
Thank you for your presentation. Amster relies on Bash and Python scripts to orchestrate the entire processing chain. When automating the ingestion of diverse data formats, what are the primary challenges in establishing the initial co-registration parameters and setting up the automated cron jobs that you experience?
I'm sorry, can you repeat the question?
Yeah. So yeah, for automating the ingestion to diverse data formats, what are the primary challenges that you experience in establishing the initial co-registration parameters and setting up the automated cron jobs?
The challenges that you meet in the beginning, it's basically the default parameters are working in most of the situation. But if you are in a region when you have, if you are using Sentinel-1, it is vegetated area, or if you are working on glaciers, and then it's maybe the parameter won't fit what you need. So that's why we also rely a bit on the expertise of users in order to have a first guess of the parameterization. It still should work, but there is some fine-tuning. So that's why we encourage people to first start with a single pair bash script so that we can work on a smaller case, and then you scale up when you basically are happy with that.
Thank you. More questions? Thank for a couple. I have one myself. For the integration in JEP you mentioned, so which kind of parameters are you allowing to the user to twin for the MBAS service?
For the MSBAS? There are some assumption in the average displacement. So you in the Tikhonov regularization, if you know about the Sergei Samsonov article, there is some different order that you can choose from 0, 1, and 2, and depending on that, it will define, let's say, that the average velocity over the whole region is 0, the average displacement over the whole area is 0, or the average acceleration is 0. So that's something you can tune. I think that by default, it's the average displacement over the whole region is 0 because, well, if you don't know, it's kind of a normal assumption. And you can also, I remember you can change the gamma parameters, but I don't remember what the gamma refers to in the MS inversion. I'm sorry, I need to check again. No, it's not so big. You have like 8 parameters to set up, and I need to check that in more detail if you want.
You said that this MS-bus algorithm can merge the data from different sources and different geometries.
Yes.
So the question is whether the data must overlap over the time, or you can also merge, for example, ERS and VSAT Sentinel data.
You can use everything you want. I mean, you can mix Cosmos Skymet with Sentinel-1, with ERS, with VSAT, with NISTAR, with biomass. We can also use pixel offset tracking. You can use everything you want, and then the inversion take that into account.
Okay, so it's there is no requirement that they must overlap over the time. For example, if I have ERS and Sentinel, for example, they are apart in a time.
You can have data gaps. I mean, temporally. I mean, and it will try to reconnect, but of course, it will make some assumption.
Yeah.
So sometimes you can have data gaps, for example. Yeah,
but technically, it's possible.
Technically, it's possible.
Okay, thank you.
Okay, time for a very last question. Otherwise, move to the next speaker. Thank you very much, Quentin. We call Ling Chang for the very last presentation of today afternoon session. So we're going to talk about co-field ground motion monitoring service. Thanks.
Good afternoon, everyone. My name is Ling Chang from University of Twente. Thanks, Mr. Chairman's introduction. So I think today you already hear a lot of open source software and also service. I still like to share what we have, which is also ground motion monitoring service, particularly designed for the Philippine community. And this work actually is under the framework of COP3 project. Later I have a few slides to show this project. It is a funded project. Together with the co-authors from University of Twente and GMV Romania and TRE Altamira in Italy and Spain, I just like to present what we have achieved. For some of you who may not really know this project, the COP3 project initiative is to facilitate the update of Copernicus dataset in Philippines. And actually within this framework, we have 3 Earth observation pilot surveys. And you also see that for this project actually particularly required to offer and also develop the open source tool and also the service, which using the open Earth observation data. For our case, actually it's on one data set. We have run this project roughly about 2.5 years, and I think it's the moment that we can share this service. So under this project, we have 3 main topics. You see that we have ground motion service, ground motion monitoring service, land cover, forest, crop mapping, and also benthic habitat monitoring. And particularly for this ground motion monitoring service, GMS for short, you see that we will explore the use of open source tools. This is already ready. So you already here we have, for instance, GMTSA, ICE, MintPy, and all the open source software which are already ready. So which is very luxury at the moment. And we will also take this European ground motion monitoring service, EGMS for short, as a reference. So we take it as, let's say, the format and also the product. We will take EGMS product as reference. And particularly, you see that we will also generate 3 different types of product, which is, for instance, the first one is the basic. So we will generate the line of sight deformation along with the deformation time series, and also the calibrated product based on the GNS observation. And then the third one is also product, which considering the line of sight decomposition when both ascending descending data set available. Before I dive into the detail, I'd like to directly give you the summary about what we have done so far. The first, we streamline and standardize the open source insert tool and the processing workflow and JS-ready output. So meaning that we apply this engineering approach and trying to explore all the possible software that we can use and create an integrated system. And particularly, we also designed the user-friendly and also stakeholder co-designed output to make sure the output can be easily ingested, for instance, by the GSS software. And also, in order to lower the entry barrier for the user, we're also trying to reduce a complex processing procedure from many to just 3 Python commands, or just 1 click after filling in the parameter input card that we offer. For the moment, till now, we have demonstrated this ground motion monitoring service over about half of the Philippine territory. And of course, we offer this resultant ground motion product as well as an open source processing tool. I directly show you this workflow. So you see that in essence, it's the lightweight command line execution tool. You can see that in order to make sure this tool is easy to install to a local computer or to the cloud computing system, we created the Docker. So the first step is to install the software based on the Docker file that we offer, and then follow with the data downloading and for instance, the sparse processing, and then generate output. So I will also explain this step for the following slide. For the first one, you see that we offer this Docker file where you can directly, let's say, install all the required software and also library dependencies on your local computer or a cloud computing system. And here I list a few. For instance, we already have the script to download the Sentinel-1 of the data, and also use, for instance, GMTSA as the foundation to do the sparse processing, and also use stamps for the PSI processing. And it's also nice, Manu also mentioned that the PyStamps is recently ready, so meaning that actually we can leave from the MATLAB. For the moment, actually, we use the MATLAB runtime to make sure that we have license-free software for the MATLAB. But the point is that when we also install the MATLAB runtime, the size for the Docker container is about 25 gigabytes, so it's quite heavy. And then you see that with this kind of simple setup, you just need to build a Docker with our provided Docker file and also run it on your computer. So it's really straightforward. And then goes to the next 2 steps. You see that usually, the user can simply specify their region of interest using KML file. So you just need to upload or just specify the directory of your KML file to show the region of interest and define starting and ending date. And then the system will automatically download data or fetch the data set from Credius. The reason why we use Credius is that Credius is not a physically download dataset. We just fetch the availability of the dataset that we specify. And also, we use this burst to stack, meaning that we don't need to, let's say, download it, or use the entire of the SAR satellite. As long as the region of interest is covered by the several bursts, for instance, only the bursts that cover this region will be processed. So this is a very, let's say, the storage efficient approach. And you will see that for this step 1, also automatically download the DM dataset. For the moment, we only use SRTM because we find particularly in Philippines, especially over the coastal region, there's some missing data for the Copernicus. So that's why we have to go for the SRTM. But the script to download the COP-DEM actually is ready. We also need to download the object data using EOF. And then we can go for the step 2 to do the sparse processing. As I mentioned, actually, we also have the PSI functionality ready. But as a demonstration here, I just show the processing flow for the stamps. And you can see, actually, we only need 1 command line to initiate and also complete the sparse processing. Regarding the output, you will see that we not only stick to the CSV format, because after the code development with a stakeholder in Philippines, in the end actually decide also use a geo-package dataset as output, because it's easy to be ingested by the ArcGIS and also other GIS software. And here, the table here, we show what kind of key parameter that we have for the geo-package and also CS file. So it's roughly similar like the EGMS product that we have. And along that, we also have metadata. So it shows the key information related to the whole processing. So you know that what's the starting ending date, what kind of DEM we use, and what kind of atmospheric phase removal method we apply. So this can help the user to understand the processing that they request or done by others. Then I also like to show or just to repeat the ground motion monitoring workflow on GOV-hosted cloud computing platform. So GOV is a company and also our partner within this project. They prepare and also create this cloud computing environment. Here you can see actually for this workflow actually also covers 3 steps that I introduced after the step 0 to install the package. And for the user, actually, they only need to, let's say, jump into step 1. So they upload the camera file to show a region of interest and specify some parameter regarding the temporal period, for instance. And then they can decide which kind of method they want to use, either PSI or SPAS, or they also want to upload the GIS observation to get the calibrated product, so they can easily jump to step 2 after the parameter configuration. And all this kind of processing will run in the backend, and in the end, they will also get the output from our server. So this is everything from the backend. I just like to show you what is the front for the user. Even I argue this is a lightweight command-based tool, but you see that we also have to create a kind of interface for the user in Philippines to make sure that they can easily to initiate or also trigger the processing. And here you can see that I mentioned that we only release some, let's say, basic key parameters. We don't really put all the parameters for the user to configure, because it could be a bit complicated based on their background for the install. For instance, to generate a P1.1 product, which only show the left side observations, you see that the user only need to define where, when, and how, so what kind of method he want to use, and which direction of the satellite orbit. So this kind of parameter is quite easy, and even they don't really have any INSA background. And then they just need to click on the execution button and then wait for the output. So as backend, you will see that all this kind of parameter configuration will trigger the command that I outlined with a red square. For the P1.2 product, you see that after generation of the P1.1 product, the user only need to upload the GSS file to let the system to recapitulate or validate the left side basic product, and then it will directly offer the product. So for this part, actually, it runs very quick, but also depend on the GSS network that user offered. And for the P1.3 also product, you see that it's same setup. What is different is that the user only need to specify the which directory of the orbit. By only select descending or ascending, the user need to select both. And then, so the P1.3 also product will be generated. As demonstration, you see that we mainly focus on 2 islands, Luzon and the Mindanao Island in the Philippines. As I mentioned, it's cover around 15% of the Philippine territory. And as a demonstration, actually, we don't really cover long time span. And for the moment, we only use 3 years as demonstration. And we're also trying to generate those 3 different products and also compare with the GIS observations in the provided by the local authority. So here's some basic information related data set that we use. For instance, over the Luzon, it is covered by the 9 Sentinel-1 themes. And between January 2020 and December 2024, you will see that we only have Sentinel-1 data available, just because Sentinel-1B was off service in late 2021, unfortunately. And for the Mindanao area, it's also covered by the 9 frame of Sentinel, also in descending from Sentinel-1A. So in the end, in total, we processed more than 1,500 star images, and which generate more than 4,000 interferogram for the sparse processing. And in line with the EGMS product, actually, we also apply the multi-looking. So in the end, the spatial resolution of the product actually 100 by 100 meter. So from this table, you see that we have some basic statistics analysis for the Luzon and the Mindanao area. So if you're familiar with the geography of the Philippines, you may know that for the Luzon, actually, there are a lot of cities, and also the capital also there, Manila also there. And for the Mindanao, actual island fully covered by a lot of greens. So we were struggling with the decorrelation over time. So that's also the reason why we're not really UPSI as the demonstration. And you also can see that for the density of the sparse result for Luzon and the Mindanao, you will see that over the Luzon actually is roughly 2 times of the, let's say, density in Mindanao. This also explains that for the Mindanao area, it has a big temporal decorrelation. So this is a map for the P1.1 line of sight product, which covers the Luzon area. And yeah, so you also see this color range for the linear velocity rate is quite large compared with the EGMS product in Europe. So you can also imagine how this kind of big deformation happened over the Luzon region. And we also have the toolkit to generate this KMSL file. So it means that a user is also able to visualize the result on their own, for instance, Google Earth app. By simply clicking any point, they can also see the time series, also some key parameter about linear velocity or coherence over time, for instance. So the figure on the bottom left shows an example. And for the Mindanao, this is also the deformation velocity map over Mindanao. So I think you are very familiar with that, so I don't spend time on this map. And when we try to generate a P1.3 product, you see that we have to trace back the even older dataset when the Sentinel-1B dataset available. So that's why we take this observation between 2019 and 2020 for 2 years as a demonstration. So for us, we apply this, let's say, standard alongside decomposition. And you can see that from, ascending the descending data set, we can also easily recognize the seismic activity. So you see that, for instance, there's a volcanic eruption triggered seismic activity happened in January 2020. And actually using this product, we can recognize this kind of cycle slip related to the seismic activities. Then this is also the product to show the horizontal and vertical component, and which covers the overlap area between ascending and descending data set. So I think it's quite standard for us to look at it. And to validate the INSA product, we also use a local GNSS observation to evaluate the quality of our observation. And for the moment, we have these 6 stations to analyze our product. Those are 4 graphs to compare the GNSS observation and also the INSA time series. And the yellow line indicated GNSS more frequent, and also the blue line indicates the INSA observation. So you can see that apparently they don't really align well. This is also what we expect because we have rather close observation, 100 meters of our product. So sometimes the GNSS that we identify may not really directly relate to the INSA observation. And I also need to confess that at the moment we only apply the geometric matching, so meaning that we only identify tie points when they have a close distance. But we don't really do the physical matching. So meaning that even they have very close distance, but maybe they just reflect different one. So this kind of, let's say, incorrect matching may also introduce error when we do the validation. But you can also see, for instance, the bottom right figure. We can see this kind of strong alignment between the GNSS and also the INSA observation. So it also means that for some of our product, let's say, they are meaningful and also kind of reliable and also validated by the GNSS observation. But still, this is still, let's say, the work to be continued together with the local authority because they have the, let's say, the instrument measurement and also the ground truth measurement. So they can help us to evaluate the quality of our ground motion product. Okay, so here I would like to summarize some take-home message. So you see that for this ground motion service processing tool, actually is open source end-to-end tool. And I think it's not only facilitated to the INSA expert, but also to the people who are interested about using the INSA tool. And if you're interested about our open source tool, you can scan the code on the top right. We already released this tool on GitHub, so you are very welcome to test it and also give us some feedback. And as I mentioned that we use Docker to encapsulate our software and also the dependency. So also meaning that it simplifies the setup and also the deployment of the processing environment. So even you only have laptop, if you have external hard drive, you can do the INSA processing by yourself. Yeah, to facilitate the local stakeholder in Philippines, we also offer this user-friendly interface, API, and with some key parameter released. But of course, if you're expert, actually, you can easily touch the core of the script to adjust more parameters that you want to change. And currently, we have this ground motion product covering 15% of Philippine territory. We are willing to share, just let us know. And also, we welcome your feedback related to our tools. Yeah, that's all on my side. Thank you so much.
We have time for questions.
So hello, thank you for your presentation. So I'm Mark Beumans from SkyGeo, and I wanted to ask you, how are you planning to do your validation kind of outside of the Malay Bay where you have your GNSS station? I saw that they were quite clustered around that bay and then not outside and not on the southern islands. Do you have a plan for the validation there?
Actually, we are co-developed this kind of validation with the local authority. Even they are not really willing to share the GNSS observations over entire of the Philippines, but actually they are willing to do the internal comparison and validation.
Thank you.
Yes, thank you.
Thank you very much. So as I saw in your study area, it's covered by several tracks of Sentinel-1 data. I was wondering to know how you managed to create a mosaic out of this overlapping region actually to handle these errors. And also you showed a map from ascending and descending results that they were not so consistent to each other. How do you interpret that in Philippines?
Yeah, thank you for your questions. Regarding the scene stitching, actually, we also have the script to do the stitching, and mainly based on the point over the overlap region. But we also use a GNSS to do the stitching. So if we have observation over the overlap areas, and we can do this kind of stitching. I didn't really show it here, but we have the script ready. Regarding the discrepancy between ascending and descending, we still suspect there could be some reason related to the arrow, probably related to the atmospheric phase. For the moment, actually, we use a standard method within GMT-SAR, which assumes the atmosphere as a noise to do the filtering. But we also have the option method for the APS removal based on the geckos, which is also ready in the script. So it's meaning that the user actually can also adjust this kind of parameter setup to have a better and a reliable result. Yeah. And one thing I also need to mention is, for the moment, we use the same parameter to do the entire processing. So this is also could be a reason for some area, maybe it looks not so, let's say, convincing for the result. Yeah.
Just a question on that point. Do you feel that having such a simplified setup means, particularly in your case, issues like unwrapping errors will start causing issues when you start unwrapping across all the islands?
What kind of error, sorry?
Unwrapping errors.
Yeah. So we do also have the parameter within the 3D unwrapping. And yeah, for the moment, we still use the common parameter setup, but user can still feel free to adjust.
Any more questions? It's coming.
I think unwrapping error is always an issue. So we don't really have a direct strategy to solve it.
Yes, I actually have a similar question. So I'm sure you will encounter a lot of unwrapping errors when you do the unwrapping of the full interferogram. So I'm just wondering if you can share some tips how you're because the results looks pretty good. So I'm just wondering if you can share some tips on how you're coping with the unwrapping errors, special parameters you use. But I assume you're unwrapping using SnapView, right?
Yes, yeah. And regarding the parameter to initiate the SnapView, we based on the empirical parameter setup. Yeah, for the unwrapping error, I think probably the colleague from Schedule also indicated this kind of anomaly detection. And if this anomaly is not from the signal from the unwrapping, actually, we can also think about using this method to identify it.
Yeah, hi Ling. I have a small question. So your users are able now to do the processing. What if in 6 months they want to redo the processing? Do they have to do all over again? Or is there a model to do the update of the processing?
Yeah, we do have the model to do this annual update, meaning that we still keep this co-registered time series, and which can help us to do the fast update. Yeah, thank you.
Thank you very much. I suggest we move to the roundtable. Thank you again.
Thank you.
Yes, for the roundtable, I invite the speakers from the chairman from the first session in the morning. So we have the opportunity to ask questions, so don't be shy. We have this unique opportunity to have the people from the different processing environments, from Snap, from JEP, from FlatSim, from Hamster, from OpenEO. So that's really your time to ask questions. If you have questions about funding open source tools, if you have questions about the future of in-source software, we talked yesterday about benchmarking. Oh, sorry. Is it good now? Okay, sorry. As I said before, we have this unique opportunity of having many people from different processing environments such as FlatSim, Hamster, OpenIO, and so on. So don't hesitate to ask questions. That's really the good time. If you have questions about funding, open sources, if you have questions about... Not loud. I will not repeat a third time, but you get the idea. So, first I have a question for the audience. I wanted to know what are the people that are processing your inside data on your own computer for science? Okay, I see some people. Don't be shy, don't be shy. Who is using the servers from the institution? Okay, much more. Who are using other cloud services such as JEP, Amazon Web Service, and so on? Okay, so it's really a good mix of every possibility. So yes, maybe we can start to discuss about the INSAR products from this morning, but also the processing environments. So again, if you have questions about this, don't hesitate, and I will give the microphone, the one which is working, to the dedicated person.
Maybe to add to your remarks, I think this round table is also especially meant to come up with recommendations towards ESA for the next couple of years to help them make the program, and they can use our recommendations. So if the audience has any recommendations regarding INSA data products or the services that were presented, please raise your ideas to maybe help steer the discussion on regarding the INSAR product part. Mario and I created 2 seed questions that we can put on the screen maybe also now to help you think in a certain direction, but any recommendation, any remark is welcome that we can convey to the organizers. So these are the 2 seed questions that we have on the products, but if you have any remark regarding the services, of course, please also raise your ideas. Yes, regarding this first question, I already asked for that. That was on a different session about these ETAT products. That why not we not introduce the ETAT correction into the data? The answer was, but that's some people need the data quicker than the ETAT product appears. But if we are talking about data from archive, why not to provide the data already corrected? And the same, like, for example, with ERS and some historical NVSAT data, why not to put these precise orbits that we have somewhere stored separately into one product? Better, you want to respond on this remark, or is a new one? Okay. Oh, both, okay.
Just for the question of ZB, not everybody wants to have products with the ETAD already applied. So then you have to basically provide functionality to remove ETAD products, so to uncorrect the products. So I think the system that we have is flexible enough. And just regarding the first point, this S is going to reprocess all Sentinel data. That is very much appreciated, but and I think it's the move in the right direction. But who is going to download all the data again? Because we are dealing effectively in a problem that is not going to scale well, and that is the bandwidth. I think on the first day, Nuno Miranda showed the slide when he is generating, Sentinel-1 is generating 63 terabytes of SLCs a day and 13 terabytes of level 0 a day. So it's a scale of factor 4 and something. So instead of reprocessing, why don't we put again a remark that's been, I think, on a Fringe recommendation for last, I don't know how many cycles, just give us the focus in software. Because I'm not complaining for myself, for my own team, for group in which I'm contributing. We have our own focus in software. But providing functionality from level 0 to level 1 will facilitate and resolve lots of issues that we will have to deal with, and we are dealing with. I understand that is not for everyone, but at least it will open possibilities to resolve many of the scaling issues that we're going to face, because we are going to deal with the terabytes of data. Thank you.
Okay, thank you, Petar. We will take your remark along. Any other?
I think I can send something to, yeah, regarding maybe downloading the entire archive again. I think you can download the ETAT product, all the archive, not the SLC entirely again.
No, but just the whole premise of basically fixing something somewhere, and okay, it's fixed, but you have to download it. I don't think that there are many people that are going to do that, because you're not processing this time series and just keep. Of course, there is an application that it will going to have particular interest in downloading data again, reprocessing and data. But I'm just going also and produce, because first sentence is then it's conflicting a little bit, because you put it's going to reprocess all Sentinel-1 data. So are we going to complete archive, or only archive that is covered by ETAT products?
Well, there's, I think, unless you know more details, I think we need to ask Nuno. Okay.
Yeah, but the recommendation doesn't change. I mean, I understand that there's certain boundaries of providing level 0 to level 1, but let's at least revisit that discussion, because we're going to also solve your problem, bandwidth and downloading the problem. So I think evolution in that direction, and RAM and hard drives are not getting cheaper for obvious reasons.
Okay, thanks, but for the record, this is my translation of Nuno's remark yesterday, so maybe I phrased it a little bit wrong, but we can double check with him tomorrow. He would be back, I think.
Yeah, I just want to comment over here. In response to that, I'm really happy the whole archive is being reprocessed, because that will also convert it to ZAR. I think having a step change in a very different format is going to be a problem for the community, and the reprocessing event lets you go back and fix all kinds of stuff that happened in the early PRFs. It gives you a new version that's much better for user access and optimized access, and will make egress easier. I think everything about the reprocessing is a good idea.
Maybe then, sorry, yeah. Maybe then two comments. So in, let's say, distributing, let's say, something that already has the ETAT applied, I believe this could be the co-registered SLC. So Mario was talking about this initiative earlier from ESA. This is kind of going back and forth, the ideas between NASA, JPL, and ESA. So NASA is now at the forefront of producing this more, let's say, refined and more analysis-ready products, but ESA also wants to catch up on that. And for those, I think we will have the corrections at least applied. So you have the co-registered SLCs, where as much as this stuff has already been taken care of to make them easier to handle, while the SLCs, they won't be touched, they will be reprocessed, as it is stated here on the slide. At least this is my understanding. And for the level 0 to level 1, maybe some of you have heard the talk of Ingvar yesterday. So it will be kind of endorsed, I believe, by ESA that the GAFA processor is fully compatible with Sentinel-1 data. It will be able to do the focusing level 0 to level 1. So if you want to do the job on your own, on your premises, this was exactly the statement that Ingvar was also making in his presentation, that downloading the level 0 and so on is much more lightweight compared to re-downloading the full SLCs again. So this is maybe a way forward for those who really want to do it on their own.
Hi, I'm Hanno Marjaars from Skygeo. A big part of the work that we do is in active mining sites. Over active mining sites, the situation changes very rapidly. Like in a matter of weeks, like big areas might, like big areas of material might have been moved. So you might end up with like wildly outdated dams over a very short period of time. So we would benefit greatly if actually there was a ready product of like rapidly updated elevation models that can actually feed into the processing chain. Because currently we are working with like, yeah, outdated elevation models or like, yeah, like very expensive, yeah, high resolution ones. But yeah, you would benefit from like maybe an up-to-date elevation product every week, every couple of weeks, every couple of months or so.
On number one, it's something that for us in the radar, let's say, world is new to have a air processing campaign, but for the Sentinel-2 world is not, because you have the collection. And at the CLMS, we are massive users of Sentinel-2, and if you have a new collection, we are obliged to reply, because if the new collection implies data improvement is then moved to improvement in the final products. And on lane coverage and use, you have to give also consistency of algorithm and products over long time series. We may be in the same situation for Sentinel-1 based products. The only suggestion that I give is something that I also said to Nuno, is that we have a clear time plan from when these batches is gonna be done, because of course it's probably not gonna be done all together. There are gonna be period X from month to month and so on, so that we can plan, let's say, properly and not have a big impact on operations.
Yeah. Driving.
Thank you. Yeah, just a clarification regarding this focusing software. What I meant was, indeed, it's good to reprocess, but we shouldn't be driven by the complete reprocessing just to comply with another format. What I meant is that, obviously, Ingvar, I'm very well aware of what he mentioned, but I think that focusing software should be becoming part of the product portfolio. That it's not going to be a one-time toolbox. It needs to become something that is maintained and part of the production or dissemination strategy or product portfolio. And also, one of the strategies that could be also explored, that you make this focusing software as a sort of unzipper, so that you make it part of the level 0. Because if you compare level 0, I think 1.5 gigabytes, software will be like 20 megabytes. So just package it up together with the product, so that when you download, you click on a button and basically it will unzip with a predefined, or at least software is a part of the product. That's what I meant. So that the software and basically is a part of the product evolution and maintained together with products. Not to say, okay, here's the software, level 0 is released, it's basically out in a community, somewhere in GitHub, it's not maintained, not endorsed, not supported. So that's the only comment that I had, because the bandwidth is nice to download, but if you download the whole territories, the whole regions, the whole continents, it becomes a lot, both in terms of time and hard drive space. And also, if this, I think it can also be a question for Nuno, because when you start reprocessing, what will be the overlap time between the reprocessing campaign? Will it be any, basically, a buffer that will have a data from the both formats or both campaigns available, and for how long? Will it be a clear cutoff? That's just a question. I understand that people in the audience here cannot answer, but that could be a question for us, a recommendation to make a very clear strategy how this transition will happen, and what Lorenzo is saying, very important also when.
So you mean to communicate clearly the
transition
path?
Because I think it happened like 1 year ago when level 1, the data stopped being compressed. So we had effectively downloading uncompressed data instead of some number of gigabytes. You download basically uncompressed images is 5 gigabytes. And if you download for the whole continent, basically it's burning a lot of bandwidth, because in some facilities, somewhere for convenience, they decide to stop zipping products. And that was never announced and never announced. So more transparency and management and a very clear strategy when this transition happens. And if you release level 0, maintain it. So basically, it needs to be part of the product portfolio.
Okay, I think it's clear, Peter. Yes. Any other remarks? Maybe on the second question or on the services?
Hello. I have a question regarding the PyStems. I've just checked out the GitHub repository and there's already some documentation there. But are you also planning to launch some sort of YouTube videos or tutorials or some sort of ESA conducted workshops how you can operate PyStems in the future?
The one I'm talking before or the one from this morning session?
The one you mentioned in this case.
The one I mentioned, I think there was an initiative from Roberto Del Prete himself, but I think he already, as you said, there's a lot of documentation there regarding videos or tutorials, something like this. I may ask him directly. I believe so. I mean, he used to get along with all the people, being able to use the tools that he releases. I think he has a several story of repositories there lived. But yeah, I will obviously let him know about the remark, but I believe that they will come. Not especially ESA trainings, but maybe they are taking, in the past, Snap to Stance, for example, was in tutorials in IGAR's couple of years. This weekend, we have also other tools being in tutorials. So depending if in the future they will come and they will put it into advanced LAN training sessions on that I cannot say no now. I cannot say yes either, but it may happen, yes.
Thank you.
Any other suggestions? Then I guess we're going to leave it with this.
Yes, sorry. Yeah. For this data-driven co-registration, when and how specification is going to be maintained, especially how these virtual masters or basically super masters or main images are going to maintain design defined, and how these reproductions is going to basically affect co-register SLCs. Mario, that's a question for you.
No, I don't know if I understood well your question.
Okay,
anyway,
let me clarify it. Where is the specification? Where is the spec for co-register SLCs?
at the moment, we are doing a project with ESA. We are developing the software prototypes, which will be open source. And I guess also the documentation will be released. Then, if these processor prototypes must become operational for producing operationally the products, this is a decision to be taken by ESA.
Yeah, just recommendation then that there should be also some kind of community consensus of how this co-registration SLCs are going to be generated, what will be the master and strategy or whatever, because I guess there will be plenty of opinions on that one.
Yeah, I mean, there is...
you ask for feedback.
There is, within the project, some meetings with the, I don't remember, the like kind of user work group, I don't remember exactly the name. We make, from time to time, a meeting with them to explain what are the ideas and to get feedback from them. I don't remember exactly the name of this group, but there is something like this. With the, yeah, you are part of the working group.
Yeah,
Yes.
yeah. You want to have a mic? Or? No, okay. I don't think that work group can decide, should decide, and about what would be the parameters for co-register SLCs. I think there should be a bit more wider consensus. So, if I understood, what do you mean? Which work group you meant? And I stop here.
Okay. Thank you. Good remark. We'll take that along as a remark regarding the second question we put here on the screen. If there are no final suggestions anymore, we suggest to close it here. We have, of course, also this afternoon a poster session, also related to the two session topics that were presented today. So please have a look at these posters. If in the next couple of days you still have some ideas that we should pass to ESA, please let one of us know, then we can take this along. Okay, and hereby then let's go to the posters, I would say.